A couple of weeks ago, Bev Try Thinking decided to challenge Scholar Sauce on the topic of spherical geometry. Now, Scholar Sauce is Alan Perry. He has a PhD in mathematics, and he is the chair of the math department at Utah Valley University. And Alan is about to give Bev a lesson in geometry and mathematics. I'm pretty sure this is not going to work out well for Bev. I'll just start it this way. Hey, what's going on, everybody? Blue Marble Science here. This evening, we've got a guest, a gentleman by the name of Alan Perry. And Alan is the chair of the math department at Utah Valley University. How you doing tonight, Alan?
I'm doing great. I'm interested looking forward to talking to you about this stuff. It'd be fun.
Yeah, why don't you tell us a little more about yourself and a little bit of what brings you and I together here.
Sure.
I'll sit back and listen.
Sounds great. So my name's Alan Perry. I'm a professor of mathematics at Utah Valley University. Like you said, I am the chair of the math department there. A little bit of my educational background. I have a bachelor's degree in mathematics and a master's degree in mathematics from Utah State University, and a second master's in mathematics and a PhD in math from Duke University. I taught for a few years after that at the University of Connecticut, and before coming to Utah Valley University, where I currently work. So I got involved in trying to make some YouTube content around COVID, around the time of COVID. We'd moved to teaching online, and I figured I had had to buy all the equipment to record online anyway. May as well start making some YouTube content. So I created a channel called Scholar Sauce that's all about trying to make mathematics engaging and fun and interesting for anybody that can go there. So I'm trying to make it accessible. I kind of feel like math sometimes gets a bit bad rap in society. People kind of tend to frown on it a little bit, and I'm hoping to make that change that a little bit. So trying to have a fun time with talking about mathematics and stuff like that. And this video here that we're going to discuss is on an interesting fact, an interesting quirk in spherical geometry, where triangles don't add up to 180 degrees. The angles in them don't, which is different than how triangles work in Euclidean geometry. And about a year after this video posted, Bev's channel, I think it's called Try Thinking. He caught wind of this video and decided to do a live stream on it, and kind of didn't understand most of what we were talking about. And so I reached out to Blue, and here we are. We're going to look at Bev's review of my video and talk a little bit about it.
Terrific. Absolutely. And with that, I'll tell you what, why don't we just get into this and see where it takes us. How about that?
Yeah.
So let's see if I can find the play button. There it is.
Well, it's not really, but math teachers do tend to leave things out that are too complicated to get at the point that you're trying to say. The lie that I want to talk to you about today is the angle sum of a triangle. Now, you probably know from your geometry classes that if you take the three angles in a triangle and you add up the measures of each of those three angles, if you do it in degrees, you should get 180 degrees.
Right, everyone, you all right with that? I'd say yes. That's there are many proofs that a triangle has the sum of two right angles, and like you said, in degrees, if you want to do that, that's 180. Many proofs. So
if you add them up in radians, you should get pi, which is the best number, by the way. But it actually
was that a little lie?
I don't think that was a little lie. I think I'll let you talk about that for a second.
This line's funny. I mean, he goes on. Let it play for just a second more.
Did he just squeak in a little lie there by saying pi is the best number?
Yeah, pi is not a number.
Okay, you can pause it. So I have to laugh at this. I mean, I'm not exactly sure what they're trying to get at here. I mean, yeah, pi is a Greek letter, but obviously the thing that I was referring to was the number 3.14, 159, etc. You know, it's the we all know it's the ratio of the circumference of a Euclidean circle to its diameter, you know, and all that kind of jazz. Here I'm talking about, you know, measuring angles in radians instead of degrees. So, you know, radian, of course, is the 1 radian is the angle measure that sweeps out 1 radius worth of arc length.
Right.
And there's 2 pi of those radians, so 6.28 of those angle measures in an entire circle. The funny thing about this particular line too, though, is that the reference to pi being the best number is sort of an inside joke because I work, well, I used to work with, he's since retired. I used to work with Dr. Bob Pillay, who's the father of the Tao movement. So I don't know if you're familiar with this. He wrote an article back in 2001 called "Pi is Wrong," and what his argument was is that we shouldn't use the circle constant of the circumference to its diameter. We should use the circle constant that's the ratio of the circumference to its radius, which would be 2 pi, and it makes some things in trigonometry a little bit more clear. And we've had in both 2016 and 2020 as kind of fun debates to pair with the U.S. presidential debates of which constant is better. And I argue for the pi side, and he argues for the tau side. So this was actually just an inside joke about it being the best number based off of that. But it's bizarre that they don't think pi is a number. I mean, it's weird to me.
Yeah,
I don't know.
Absolutely weird. It's convenient to write a Greek letter like that. We do it all the time with all kinds of things, but it's just a constant. That's all it is. We can get rid of pi altogether, and every time write down 3.1415928, whatever, you know.
Yeah.
That gets laborious. It's easier just to write pi.
Yeah.
Or tau.
Or tau if you want to use 2 pi, but we're not in that camp.
That's right. That's right. We're on the pi side. But yeah, I thought that was hilarious when that guy said that. Pi is not a number. What the hell does he think it is? Okay.
Yeah, it was bizarre.
Yeah. We'll keep going.
So yeah, I'd say yes. By the way, on the point before about, you know, whether this is a proof, you know, all angles of a triangle adding up to 180 degrees. We also had a university professor. I think one of his comments was that if you didn't have that as one of your, let's say, axioms, self-evident truths, that you might be a fool. I think he said that. I think there was a song about that as well.
Can you pause it there?
Yeah, it's
yeah. There you go.
So this is an interesting point here that he makes too. So the notion of an axiom is not what they presented here. Now, it is true that in some contexts, when you use the word axiom, it means self-evident truth, but that's not how mathematicians use the word axiom. You can even look this up in a dictionary. It has a special definition for mathematics. In mathematics, an axiom is more like a ground rule. It's a basic assumption about the type of thing that you're going to talk about. So when, like, for example, with Euclid's postulates or axioms, when he writes those down, he's saying, this is the space that I'm going to talk about, is a space that follows these rules. He's not saying that these rules are true in every possible context. He's just saying that this is the context in which I'm going to talk about and prove things about. And we have lots of different axiomatic systems that are built on these kinds of things, and not everything satisfies all these axiomatic systems. You can look up things like groups and rings and fields and vector spaces and topologies. All of these are axiomatic systems that are all built on axioms that are, when we write them down, we're saying this is the type of space that we're talking about, and the theorems that are true are only true within the context of that axiomatic system. If you leave that axiomatic system, it might not be true. So, for example, a theorem that's true about a ring might not be true about a vector space or a topology or something like that. And so here, when I'm saying, when he refers to this axiom here, that this university professor was probably talking about, I have no idea what the conversation he had with the university professor is, but just trying to read between the lines of like, what would they have been talking about? probably saying that that's one of the axioms that you could assume that's equivalent to the Euclidean parallel postulate that would guarantee Euclidean geometry. But if you don't make those assumptions, you can have all sorts of different kinds of geometries, and that's actually the heart of what this conversation is about.
Yep, exactly.
Again, the triangle axiom, it's there, it's an axiom, and of course, there's many.
I'm going to pause it again right there because there's something else interesting. Bev continues to call it the triangle axiom or triangle postulate. And when he does that, I want you to know that what he's referring to is Euclid's fifth postulate. Bev somehow or the other interprets that as meaning because the lines intersect on one side, that forms a triangle. That was not the intention. That's not what that says.
Yeah. And actually, this one's kind of... Oh, go ahead.
No, go right ahead.
Yeah. So what I was going to say about this is I think this misunderstanding here, or this mislabeling, is almost understandable if he misunderstood it because of the following. So Euclid's fifth postulate is really talking about parallelism,
right?
And it's citing a scenario when two lines end up not being parallel. They do happen to form a triangle, but that's not what I think well, I don't know. I have no idea where he got the term triangle from, but the thought that I had that he could have had is that if you assume the first four of Euclid's postulates, then there's a lot of statements that are equivalent to the Euclidean to Euclid's fifth postulate, and one of them happens to be this angle sum triangle postulate kind of thing, that the angle sum of a triangle is 180 degrees. If you assume that and the first four of Euclid's postulates, and also fill in the gaps, because Euclid's elements is it's not really up to modern standards of rigor. I mean, it was the first time anybody ever wrote anything like this down. And so he makes a lot of assumptions that he doesn't state and stuff like that. And in more modern treatments of Euclidean geometry, we kind of fill in those gaps. If you fill in all those gaps, but essentially assume just what Euclid intended by the first four postulates, then Euclid's fifth postulate and the angle sum of a triangle having 180 degrees are logically equivalent. One implies the other and vice versa. And so in that sense, if that's where he maybe read something somewhere that said, hey, this triangle thing is the same as Euclid's fifth postulate or something, then maybe I could see it, but I don't know. That's the only thing I could think of where he got that term from.
Well, I want to say too that a lot of what Euclid had to say was rather loose, I guess would be a good term. There are a lot of things that, as time has moved forward in the last 2,500 years or whatever, we've got much better definitions these days of some things. Euclid didn't seem to make, maybe he did, but you can argue he did or he didn't, but he'll talk about a ball in one spot and then he'll talk about a sphere. We separate those things into two separate things. Mm-hmm. The sphere is the surface that encloses the ball. That's the way I learned it.
And that's correct. That's how we treat it in mathematics.
Yeah, we treat it that way. The sphere is just the boundary between the ball and everything outside the ball.
Yeah.
So.
And by the way, I totally agree with you with the situation with Euclid. One thing I do want to point out here is I don't want to make it seem like we're trying to crap on Euclid. What Euclid did was foundationally groundbreaking at the time. I mean, it was just absolutely like cutting edge at his period of time. Nobody else at that point, as far as I know, had ever tried to construct geometry from a set of first principles, or really tried to construct anything from a set of like axioms. And so this, Euclid, he makes a lot. It's funny. He makes a lot of the same kind of mistakes that we see students make when they first start learning how to proofwrite. A lot of things are assumed that really shouldn't be assumed and stuff like that. But what he did just got the ball rolling on how to talk about rigor. But you're right. It's been 2,000 years. We've gotten way better at making precise statements since then. And if you read you read more modern treatments of Euclidean geometry, there's a whole bunch of different sets of axioms that you can do. and the smallest set that I've seen, at least, seems to be about seven. I think seven axioms long, including Euclid's Euclidean parallel postulate. Maybe it might be 8 if you include a transformational one, but some of them are even longer than that. And it's even worse if you try to get into like three-dimensional Euclidean geometry.
Yeah.
Because Euclid's, that's the other thing to realize, is Euclid's 5 postulates describe two-dimensional Euclidean geometry, not three-dimensional. In his later books, in the very last 3, he does talk about some three-dimensional shapes and stuff like that, but they are not sitting in the same postulate framework that he set up in his first 6 books. And to get enough axioms to describe 3D Euclidean geometry, I think I saw one set one time is like 23 different axioms that you have to assume in order to get it. It's complicated.
Yeah, when you get into the later books, he mentions a ball and a sphere and things like that, but he says very little about it.
Right.
He didn't really ever try to address that spherical surface because it doesn't work.
Yeah.
It doesn't work.
Well, and I think actually, so this is an interesting thing that I found out about some of this, is that Euclid did actually write about spherical geometry later. He has a work called Phenomena.
Right.
Yeah. And it's an astronomy work. And I mean, Euclid talked about it, spherical geometry there, because I mean, the Greeks knew that you couldn't use planar geometry to describe, astronomy and stuff like that. They knew that it was going to be spherical. And I think there's even, so I'm looking at the Encyclopedia Britannica's article on non-Euclidean geometry. This is where I'm getting this quote from. But about 400 years after Euclid, there's a Greek astronomer named Ptolemy. He wrote a book called Geography, and in it he says this: it's been demonstrated by mathematics that the surface of the land and water is in its entirety a sphere, and that any plane which passes through the center makes at its surface, that is, at the surface of the earth and of the sky, great circles. So they were already using this like spherical geometry stuff that this video is about to talk about, the earth and the sky. And that was back in like 150 CE. So it's, way back then.
Oh, yeah.
But Euclid wrote about that stuff too.
In fact, even Euclid, I think somewhere in, I don't remember which book it is now, in the Elements, but even Euclid mentioned, this was something funny that I also heard Bev, and you're going to hear it again here in a few minutes, where Bev laughs at the idea of a great circle. Well, Euclid basically described what that is. It's the largest circle you could draw on the surface of a ball. Yeah. That's what a great circle is. And Euclid recognized it.
Yeah. Another way to characterize it is that it's any circle on the surface of the ball, on the sphere, that has the same radius or diameter as the sphere.
Right.
Too, which is how you get the largest one.
Yeah. That's another way of saying it. Yep, exactly.
Yep.
Okay, let's see where else he goes here.
Any proofs that triangles have 180 degrees. And of course, we're dealing in a logic-based system where the law of non-contradiction applies, right? You can't, if there's proof that triangles have 180 degrees, then that's it. There's proof. You can't undo a proof with another proof of triangles having more or less or whatever, something other than what has already been proved to be true.
You pause it here.
Yep.
So this is, he's not wrong in the sense that you can't undo a proof. That's correct. But the thing that he seems to be grasping on is that the conclusion of any theorem is true everywhere. Theorems are written in an if-then kind of context almost always. They have a hypothesis that you assume initially, and then you prove that hypothesis implies a conclusion. And this statement here that a triangle has 180 degrees, that theorem itself doesn't state a hypothesis, it is understood to be done within the context of the axiomatic system that it's in. So you don't restate the axioms every time you prove a theorem in an axiomatic system, but those are always assumed to be, requirements of the hypothesis. So any theorem, like the theorem about the angle sum of a triangle being 180 degrees, is really a statement that in the context of Euclid's 5 axioms, or the context of Euclidean geometry, within that framework, then the angles of a triangle add up to 180 degrees. If you remove the hypothesis and you're outside of that axiomatic framework, you no longer have the conclusion to that theorem. And it doesn't disprove the theorem or anything, because the theorem said that in the context of Euclidean, you get that triangle angle sum. But if you're not in the context of Euclidean, the angle sum could be anything and it doesn't contradict the other theorem. So he's right, but he doesn't understand that there's different contexts and different hypotheses assumed to a theorem. It is true that when you prove something, you can't unprove it.
And when we talk about
this come from
whoops, and when we talk about spherical surfaces, we're no longer talking about Euclidean space.
Right. And in fact, spherical geometry fails multiple of Euclid's postulates, not just the fifth. For example, it fails the intent of Euclid's first postulate. So Euclid's first postulate is that between any 2 points, there's a line. One of the holes in Euclid's discussion is that he should have said that there's a unique line between 2 points. He actually uses the word straight line because he uses the word line to mean something else. But because he doesn't include the word unique, you could maybe say that there could be more than one, but he explicitly uses that as like an impossible scenario in later proofs. He kind of has a hole in his axioms there. But so what he intended, though, was that between any 2 points, there's exactly one line or a unique line between those 2 points. And if you're on a sphere where the lines are great circles, if you take 2 antipodal points, so 2 points that are exactly opposite each other, there's an infinite number of lines between them. So it actually fails Euclid's first postulate. So you're well outside of the realm of Euclidean geometry when you're talking about spheres. And so all the theorems that Euclid proves about Euclidean geometry are potentially false on the sphere. Not all of them turn out to be, but there's nothing about the discussion about Euclidean geometry that applies to the sphere, because the sphere doesn't satisfy doesn't satisfy the complete set of axioms. So you'd have to reprove everything from the ground, from the ground up, starting with the axioms that are true on the sphere.
And not understanding the Euclidean proof system.
Have to excuse my snarky comments here. Yeah. Sorry, Biff. I couldn't resist.
I know we're sitting here kind of pushing back on Bev, but in fairness, like it's pretty impressive to find somebody these days who actually wants to read Euclid's Elements. I think that's kind of hard reading for some people. It used to be pretty common to be required at university level back like 150 years ago. It's kind of fallen a little out of favor. It's not really considered to be the height of mathematical reasoning anymore. That's a whole discussion for another time. I'm actually working on a paper right now with a couple of colleagues of mine talking about how mathematics kind of shifted towards this race to understanding calculus and has become very calculus heavy as opposed to being geometry heavy, which it was for like the 2000 years after Euclid. So credit where credit's due. It's cool that Bev's trying to read Euclid's Elements. I think that's a positive thing, but I think he's grossly misunderstanding a lot of of how Euclid's logical system was built on, and especially what axioms are and how they're used in mathematics. That's kind of unfortunate, but
yeah. But that's that's the approach, and there's much more outside that. You just open the door, Bev, and walk through. There's a whole world out there, and you're ignoring it. You're only looking at what's sitting on the table right in front of you.
Actually turns out that fact depends upon the geometry that you're in, and it's only true if you're in a flat space.
Right. Now,
flat space?
Yeah. He says that the geometry that you're in, and then it says it's only true if you're in a flat space. Well, space is 3-dimensional. We live in Euclidean 3-dimensional space, as dictated to by Euclidean geometry. The proof-giving system that tells us that triangles have 180 degrees and pi is the relationship between the diameter and the circumference of a circle.
So this is an interesting misunderstanding and maybe a slight failing on my part for using the word space and not realizing that it's kind of jargony. So the problem is this, right? I mean, so you could talk about a one-dimensional point, zero-dimensional point, a one-dimensional line, a two-dimensional surface, and a three-dimensional space. And then what do you call a four-dimensional thing? You know, maybe you call it a hyperspace. Okay, cool. What's a five-dimensional thing? Or a six-dimensional thing? What do you have words for those? Seven-dimensional or eight-dimensional? Well, you know, in mathematics, we deal with very high dimensional types of things, and there's not really good words to keep coming up with a new word for every dimension. So we kind of just said, screw it. We're just going to call everything a space. Like, so we talk about, like, for example, vector spaces are spaces that have, linear spaces that have dimension. They follow certain rules or whatever. And so, and the dimension just refers to how many vectors are in a basis for that space. And now I'm getting even more jargony, right? Talking about linear algebra, which is probably a topic that not everybody knows a lot about. But in that case, we're talking about, you can have a zero-dimensional vector space or a one-dimensional vector space or a three-dimensional vector space, right? And we just call them a space. The same is true about topological spaces. You can have one, two, three-dimensional space, that topological spaces, and we just refer to them as spaces. So when I'm saying here that you're in a flat space, I'm actually referring to a n-dimensional, well, or heck, if you want, a two-dimensional manifold, which is a topological space that doesn't have any curvature, intrinsic curvature. So like if you wanted to get really precise as to what I'm talking about, you'd have to get into like some really heavy mathematics, and it's not really necessary if I'm just talking to if I'm trying to make this accessible to regular people. So the idea here is that I'm just referring to a flat in the sense of like no curvature kind of space. And you can have a flat one-dimensional space that would be a straight line, or you could have a curved one-dimensional space, which could potentially be a curvy line, although there's some difference between intrinsic curvature and extrinsic curvature and a few other technical ideas that I'm getting a little bogged down in. But dimension itself, is this where he talks about dimension, Blue? Or is that a little later?
I think it may be a little bit later.
Okay, well, I'll hold off on the dimension. We'll get back to this, but
I forget now. It may be coming up here in a second. We'll find out. Let's listen and see.
Sure.
So, and he agreed, and he did say that it depends on what the geometry that you're in, right? Implying that you're in a certain geometry. Well, can we be in? I mean, maybe we get the take of other people, but can we be in any other geometry?
You pause it there. So this is a weird thing that he's pointing out. I mean, obviously, I'm not saying that humans are somehow can leave the geometry that we currently exist in or anything like that. When I said which geometry you're in, obviously I meant which geometry that you're considering, or which geometry you're talking about, or which geometry you're trying to describe the mathematics of.
Exactly.
I just used a colloquial term for it. So it's weird that they're taking such a strict linguistic stance on that. I mean, okay.
What we're dealing with here is going to come into people should be able to see. We're not dealing with mathematics as you would understand it from schools, and writing down numbers and equations and stuff. And the understanding that you were taught in schools is that triangles and squares and circles, they all have a relationship in reality to the essence of what you call these things. Well, they're all Euclidean, and a straight line is a straight line.
So yes, I'm not sure where he is really getting this. This is where I think the confusion about what an axiom is running him afoul again. So he's saying that the stuff we learned in school or whatever is fine. We do learn Euclidean geometry in school, but we only teach that particular context. Again, to what we were talking about before about being able to be outside of that context. And that's actually kind of the joke that I play at the beginning of this video about the idea that math teachers lie to you all the time, what I really was talking about is they hide context from you, and to keep things simple. So they start really simple by saying, we'll just talk about this context, which is the context of a piece of paper, or spread out infinitely. And that's the geometry that we'll teach you. But we hide that there are other contexts. And that's actually literally what this video is about trying to explain that there are other contexts than what you were taught in school. And in those other contexts, different things are true than what are true in the small context that you were taught in school. There's nothing that said that Euclidean geometry is the context of reality. I mean, yeah, there's a lot of reality that does behave like Euclidean geometry, but we'll talk about this maybe a little bit later in this video. But do we actually live in 3D Euclidean geometry? Technically, no, we don't, and we can talk about that in a minute. But yeah, and especially with the notion of Euclid, I mean, when we talk about Euclidean geometry, typically we're talking about Euclidean planar geometry, which is just the geometry of a piece of paper, which we also don't live in, but we teach that context. That's kind of weird, but
yeah, well, it's the foundation. That's where we begin. Yeah, that's how we begin to understand geometry.
And here's
we need to understand that part of it first. Afterwards, we can start looking at I can see just sitting here on the desk a number of curved surfaces that can't really be described in Euclidean geometry.
Well, and here's maybe a good example of kind of what I'm getting at in terms of everything being context specific is the difference between 2D Euclidean geometry and 3D Euclidean geometry. In 2D Euclidean geometry, parallel lines are defined as simply lines that don't intersect.
Right.
But when you talk about 3D Euclidean geometry, that definition is no longer sufficient. Most of the things that are true about parallel lines in Euclidean geometry are not true about lines that don't intersect in 3D Euclidean geometry, because you can have lines that don't intersect that are not parallel.
That's right.
So in 3 dimensions, you have to have a stronger definition of parallelism in order to still maintain those same theorems. Like, for example, parallel lines stay equidistant from each other. That's true in 2D Euclidean geometry, it's true in 3D Euclidean geometry, but in 2D Euclidean geometry, it follows just from a definition of the lines not intersecting. But in 3D Euclidean geometry, skew lines, which is what we call non-parallel lines that don't intersect, don't stay equidistant from each other. And so if you just use the definition from 2D, you'd run into a false theorem. Like that statement is no longer true.
That's right.
In 3D Euclidean. You have to add in that the two lines are parallel if they have like the same tangent direction or same tangent vector. Their vectors are the same. They're moving the same direction. When you do that, then you can make a claim about them being equidistant, and that's true in that context. But you had to strengthen the definition because you changed context.
This man here seems to be flippantly saying you can just swap and change your geometries, meaning the space that you're in.
No, Bev, we're not saying that at all. That's not at all what we're saying.
Right. We're just saying that you can change which context you're considering or which context you're going to describe the mathematics of.
Yep.
And you can change that all you want. I mean, can you change what geometry you physically exist in? No, you can't change that geometry. But you can certainly change which one you're talking about.
Yeah, well, I can easily change whether I'm talking about that whiteboard behind you,
right,
or the spherical surface that's sitting on the globe that's sitting on the disk in front of you. That's two different things.
Mm-hmm.
That's what you're talking about. Bev doesn't.
Exactly. Yeah.
Yeah, let's see. Oh, look, I said something like that.
Hey, look at that. That's the same example.
He can control it, it sounds like. I want to go over that again.
Which is the best number, by the way. But it actually turns out that fact depends upon the geometry that you're in, and it's only true if you're in a flat space.
Is this man a flat earther talking about flat space? I mean, is there anything more ridiculous? What's a flat space? Flat. It
so
doesn't
go
matter.
ahead and pause it here. This is kind of curious. So there is a notion of a flat 3D space versus a curved 3D space. It's hard to visualize because the way we tend to visualize curvature is how we view it within like 2D curved objects sitting within a three-dimensional space. That's how our brains are wired to visualize things, because that's similar to the universe that we live in. But mathematically, you can talk about a curved 14-dimensional space versus a flat 14-dimensional space. We have definitions of curvature that are independent of dimension, and you can compute these kinds of things. This is actually the substance of differential geometry and Riemannian geometry, specifically, and semi-Riemannian geometry, which is what's used to talk about general relativity. For example, in general relativity, the idea is that the four-dimensional space-time, which is three spatial coordinates, one time coordinate, is a semi-Riemannian manifold that is not flat. So it's curved in 4 dimensions. Now, can you observe that when you can only visualize 3 dimensions? Of course not. That's why everything kind of looks the way that it does. But we can actually detect it. One of the things that I don't know if I don't think he gets to it, but one of the most fascinating things about general relativity is the fact that how your clock runs depends upon how fast you're going and how close to gravitating objects you are. And that usually it doesn't make that much of a difference for people on the surface of the earth. Like, just because somebody's traveling at 60 miles an hour down on the freeway or something like that, their clock's not going to change enough for you to notice. But it does make a difference for GPS satellites. How fast they're going versus it makes the clocks makes their clocks, I think, slow down a little bit. And then the fact that they're further away from the center of mass of the Earth actually makes their clocks run too fast. And the net difference between those two things is an overall that time runs a little faster on the satellite than it does on the Earth's surface. And so in order to keep clocks synced on GPS satellites to the Earth's surface, they have to artificially run clocks slow on the satellite. Otherwise, it won't stay synced with your clock in your car when you're trying to run directions. And if they didn't do this, GPS satellites would be completely useless within like a matter of hours or days or something like that.
Yeah,
because
just
the errors
hours,
would pop up
actually.
so
Yeah.
much. Yeah, I think it's just hours. Yeah.
Yeah.
So this is a fascinating thing that what you're detecting there is 4-dimensional curvature. Like the 4-dimensional coordinate system that you live in is curved, and that's causing the 4th dimension coordinate, the time coordinate, to measure differently for the satellite than it is for us on the Earth's surface. And that's curvature. That's a 4-dimensional curved space. And so, yeah, you can totally have a flat 4-dimensional space. Like that's kind of what Newton thought the universe was a flat. I don't know if he phrased it this way, but the way he treated it mathematically was a flat 4-dimensional space with 3 flat 3 dimensions and 1 flat time dimension. He didn't phrase it like this because the mathematics to talk about curved higher dimensional things hadn't been developed yet. So we didn't really know how to phrase it. But the way he solved things was treating it within that context. So that is what he assumed, even if he didn't say it that way.
Anything. But to tag flat, it's almost like somebody saying that the surface of a ball is 2D, right? These are the real flat earthers. They think space is flat.
So here's the part that we got to. I thought it was a little later. So what do mathematicians mean by dimension? I actually have a fun little short on my Scholar Sauce channel that explains this in 1 minute. But essentially, what dimension is to a mathematician is the number of is the amount of numbers required, or number of coordinates required to indicate a location on the space. I think that's the simplest way to describe it. So if you're on a surface of a sphere, like the Earth's surface, how many numbers does it take to identify a location?
2.
2, a latitude and a longitude. If you're in a curved space,
Whoops. Sorry.
and yeah, that's fine. But and so, like, for example, like if you have same thing with like a curve, right? So like you remember those old Family Circus comics where they had the little boy and he would like, he was supposed to be going and getting like the newspaper or whatever, and he ended up walking around the whole neighborhood, and it'd have a little dotted line path behind him.
Yeah.
Do you remember any of those?
Yeah. Oh yeah.
Yeah. So that's a really curvy, wonky, path. Some of it self-intersects and does a whole bunch of things. That path is one-dimensional because you can identify a location of where the kid is on the path by how many dots he's walked past, right? So that one number tells you where he is on that path. That's what makes it one-dimensional, is the fact that it only requires one number to indicate a location. It's also why a point is zero-dimensional, because there's only one location, so it doesn't require any numbers to indicate a location. So that's why it's zero-dimensional. You can make this a little more precise. This is slightly hand-wavy. If you want the really precise definition, the dimension of a topological space or topological manifold is the dimension of its tangent space at any point, the dimension of the vector space that is its tangent space at any point. So if you think of on the surface of a sphere, if you take a point on the sphere and you think of every possible tangent direction on that, like you have to kind of almost think the multivariable calculus kind of place is probably where you first learn about this kind of notion. You get a tangent plane, right? And all the vectors, the possible vectors that are tangent to the surface of the sphere at that point, form a two-dimensional vector space. And that's why we say it's a two-dimensional object, because it turns out that the dimension of the tangent space for a topological manifold doesn't change as you move around the space. So anyway, so it ends up being that kind of thing. You can do this with a curve too, right? At any point, you have a single vector for its tangent vector or a tangent line. That line is a one-dimensional vector space. And so the curve is one-dimensional. Same thing's true about three-dimensional space. A three-dimensional curved manifold is three-dimensional because it has a tangent space that's a three-dimensional vector space. But that's way too complicated. So the easiest way to just think about it is how many numbers does it take to identify a location on a space? That's the dimension.
Yeah, right.
If you're in a curved space, the angle sum of a triangle is not 180.
But like in reality, there are both straight and curved within the space that we live in, right? Because you may be thinking, what's he talking about, flat space and curved space? There's flats and curves in reality, both of them. Does that mean we change geometry? No, it just means you're in Euclidean.
Yeah, it does mean we change geometry. You're talking about the curved space versus the flat one.
Yeah, you just changed the geometry, Biff. You just changed it. Yes.
Yeah.
Again, another of my snarky comments. Please draw parallel straight lines on a spherical surface for me, Biff. Euclid says you can do that.
Yeah, and it's basically just the idea, like, to talk about a triangle in 3D space, you'd have to define the plane that the three lines are in, right? Which is a two-dimensional subset of the three-dimensional space. And that two-dimensional subset, that plane, does satisfy Euclidean planar geometry.
Exactly.
But the surface of a sphere is also a two-dimensional subset of the 3D space, and it does not satisfy Euclidean planar geometry. And that's, so yes, in answer to his question, yeah, you can have flat and curvy things sitting inside 3D space. And if you restrict your attention to just that flat or curvy 2D, 1D thing, yeah, your geometry can change dramatically on each of those things.
So what is the problem? Why he's reducing space to plane or curved surface? I don't know. Both of them are in Euclid.
In fact, there's two different types of situations that it can run into. But the first one that I want to talk about is probably the easiest one to understand, and that's the sphere. The sphere is a curved space, and if we want to draw
No, the sphere is a ball. In reality, in Euclidean space, you can consider
go ahead and pause it
the sphere.
There. The weird, I apologize for pausing it like every 2 minutes, but this one's kind of going what you said earlier about the sphere being the boundary and the ball being the interior is exactly right. But it's funny to me, like, so he says that the sphere is, he uses that to argue that the sphere is not curved. I mean, like, even if you had a ball, the outside of it's still curved. And the inside, yeah, is just a 3D subset of 3D Euclidean space, but the outside's still curved. It seems a little weird to me that that's his argument, but anyway.
Yeah, I didn't understand that either. Hence the comment I made. I mean, really.
You can consider the sphere a ball. Like, everybody's heard of a ball. That's a sphere within Euclidean space.
Well, that's another point that Bev doesn't quite understand. There is a difference between a ball and a sphere, but I'll let you talk about that.
Right. Yeah, definitely. There's a difference between a ball and a sphere. The sphere in mathematics, we use the term sphere to specifically refer to the surface of, like if you're talking about the Earth, the sphere of the Earth would just be the surface of the Earth. The ball would be the interior, and you could either have an open ball or a closed ball. If it's an open ball, it doesn't include the boundary at all. A closed one would include the sphere and the interior ball. And then, of course, could include portions of it, I guess. But anyway, yeah, the difference between a ball and a sphere. The sphere is just the surface. The ball is the interior. And that's how mathematicians use those terms pretty exclusively. I mean, yeah, occasionally they might slip up and say it because I understand the confusion here because colloquially we might use those terms interchangeably.
That is right. I think that's where some of the confusion comes from.
Yeah.
Colloquially, we do tend to mix those up. But technically, to be very precise about it, the sphere is the surface. It is a boundary. It is that which separates the ball from all of the things outside the ball.
Yeah. You think of it like this, the leather of a basketball is the sphere. The air inside the basketball is the ball.
Mm-hmm.
Yeah. But the other thing that's kind of
read the definition read the definition of what a sphere is, and it's all of the. I'll try to paraphrase it myself. It's essentially all of the points that lie an equal distance from a center point.
Mm-hmm.
It is that collection of all of those points, and there's yet another another way of saying it's only two-dimensional. Those points are no dimensions, but when you put them together, you make a surface which is two-dimensional.
Right, and your definition there, the first one you gave is spot on too. Like you can see that's talking about just the outside, because if it's just the points that are exactly a distance equal to the radius away from the center, none of the interior points satisfy that condition. So they're clearly not included when you're talking about the sphere.
Clearly.
Yeah. One of the things too that he mentions here, which is kind of funny, like he says that, the sphere is inside Euclidean space. That's fine. Like the fact that it's embedded or inside Euclidean space does not make the object itself Euclidean. If you restrict to just that subset of the sphere, it does not satisfy Euclid's 5 postulates. And so it's not Euclidean. You can have non-Euclidean objects sitting within a Euclidean ambient space because, the ambient space is including all the stuff around that subset too, not just the subset. If you restrict to just the subset, that's a totally different discussion.
Yep.
Welcome everybody. If you're just joining us, we're going over a video of a guy's called Scholar Source. And the angle sum of a triangle is not capital letters 180 degrees question mark.
So Scholar Sauce, please like and subscribe.
I'd say he's already fallen into stolen concept sort of realms quite a few times.
A triangle on that curved space, we have to build it out of lines that are on that space. Now, if you watch my previous mathematical misconceptions video, you'll know that the lines on a sphere are actually the great circles.
Right, so the lines on a sphere are great circles. Now, luckily, we've all been within this, talking about this for quite a long time, the understanding of how this works. But we watched the Veritasium video the other day, and in that Veritasium video, what this guy said was that in spherical geometry space, a point becomes 2 points, antipodal. A line becomes a circle, like he's just said, a great circle, because giving it extravagant names seems to do something else. It's just a circle.
Yeah, a great circle, of course, is, like you said, the largest circle that you can draw on a spherical surface. Another way to describe it is it's a circle that has the same radius or same diameter as the sphere itself.
Yep.
And the reason why it's a line and in a sphere is that it's the shortest distance between 2 points on a sphere. If you are trying to traverse, if you have 2 points on the sphere and you're trying to get from one to the other and you cannot leave the surface, you can't bore through the middle of it, you can't fly over it, you have to walk on the surface, the shortest distance, the shortest path between those 2 points is following a great circle, which is actually kind of an interesting thing, because like if you look at latitude and longitude lines, all the longitude lines are great circles, but the only latitude line that's a great circle is the equator. This is a curious thing that you can even check on Google Earth. Like if you go to latitude lines that are north of the equator, like say the 47th parallel, which is the northern border of the United States, I believe that's 47th parallel, and you try to compute the distance between two cities that are kind of far apart there, you'll notice that the line that you draw between them on Google Earth to try to compute the distance of doesn't follow the latitude line. It's because the latitude line is not the shortest distance between those 2 points.
That's exactly right. Google Earth draws great circle routes.
Yeah.
Or great circle segments.
Yep.
So try to do that on Google, any place you pick on Google Earth except the equator. Try to make try to draw a line that follows a latitude line. You cannot. It will not.
Yeah.
In the northern hemisphere, it'll always be north of the latitude line.
Yep. And in the southern, it'll always be south.
And it'll always be south in the southern. Yeah.
Yep.
Yeah.
Absolutely. And that's what we're getting at here, is that's why we use a great circle, is because it's that shortest distance, or really straightest possible line. Like like I was going to say that it's like what we talked about before, but I realized that wasn't part of the recording. So probably cut that part out. But so what I was going to say here is the idea is, like, how do you make a straight line, right? That's the other question, is what makes a line straight in Euclidean space? Because Euclid's definition of it being just a bunch of points that lie evenly on next to each other isn't very precise. Like, it's hard to explain what that is. So, like, ask yourself, what makes a line straight? If you had to describe it for someone, how would you describe a straight line? And it's actually kind of challenging to come up with a definition that doesn't, like, depend on straightness. But there is one in calculus. You can describe a straight line in Euclidean plane, in the Euclidean plane, as so in calculus we talk about rates of change, how fast something's changing. We call these rates of change derivatives. So you can talk about how fast a curve is changing as its first derivative. You can think of this as like velocity, or how much that position is changing, or whatever. And the second derivative, which is how fast the first derivative, or the slope, is changing. Maybe I'll say that again. If you're looking at a line, the first derivative is the slope of that line, or for a curve, it's the slope at any given point. So which way is it going at that point? But that slope can change, and so you can measure how fast that slope changes by taking another rate of change, or a second derivative. And a line can be described in calculus as a curve whose slope doesn't change. So its first derivative doesn't change. Since there's no change in its first derivative, the second derivative, which is measuring how fast the first derivative changes, will be equal to 0. And that's what we do on the surface of a sphere like this. We calculate geodesics, which is what we call these straightest possible paths, by looking at derivatives that exist on the surface. You can't do a flat derivative, because you'll leave the surface if you try to move tangentially. So you have to have a correction term that keeps you on the surface as you're moving around. So we have a different notion of derivatives called a covariant derivative that takes into account the fact that you have to stay on the surface. And if you look at that derivative and take a second derivative of a curve there, that being equal to 0 is how we actually define a geodesic in more advanced context. So that literally is straight by the definition of that surface that you're on. So a great circle may not look straight to you and I, because we are thinking of things in 3D Euclidean space, where straight is just 0 second regular flat derivative. But from the context of that sphere, that it has a 0-second derivative there on that surface, and so it is as straight as it possibly can be. And that's why if you try to walk in a straight line on the Earth's surface, that's what you follow.
And the plane becomes a sphere. So if you can imagine you're conceptualizing a plane as a sphere, then good luck to you. But I'd say don't even bother. It's a sphere. It's a Euclidean ball. Don't try and imagine that the geometry is any different on the surface. The surface is literally where they perform the mathematics of spherical trigonometry.
So that was just wrong. Everything he just said was wrong.
Yeah, I think he's just basically. I didn't see the Veritasium video, but just given what he's talking about, I think they were quoting him that a line becomes a circle and the plane becomes a sphere. I think it's just a simplistic way that Veritasium was trying to describe the differences of how you would talk about that geometry. That the plane is just a collection of all the points that you're considering. In this case, this collection of all points that you're considering would be the sphere. That's what he was kind of getting at.
Yeah, probably.
When you talk about trying to draw a triangle on a sphere, you're talking about trying to draw a triangle where the sides are great circles. These are the straightest possible paths that you could draw. In fact, if you tried to draw a straight line triangle on the surface of the Earth, you'd actually draw a great circle triangle. The angle sum on that kind of triangle, it's not 100.
So what he's showing there, right, is the angles will be measured between the planes cut internally through those circles cast, right? Because the circle makes a plane and the angles can be measured between the planes of the circles that he's imagining. Now, for some reason, he imagines that's not Euclidean. Well, it is. It's an angle as described within Euclidean geometry through three planes described perfectly within Euclidean geometry.
Yes, and these three.
So here, they actually do say something correct here. The angle that is measured here is the angle between the two planes that are formed by that great circle.
Yeah.
I describe it a little later in the video as being the angle between the tangent lines of those circles, but those tangent lines sit in those planes, and so it actually still works that way.
That's right.
The problem is, of course, is that in order to discuss it that way, you'd have to talk about, if you're going to talk about the angles between the planes, you'd want to talk about the angles formed by two vectors that are in a perpendicular plane. It gets more complicated than it needs to be. But he's not necessarily wrong that that's the angle that I'm measuring. But just because an angle has a counterpart in Euclidean geometry, or happens to be the same angle as you'd measure in Euclidean in some other, in some other like intersecting region here, like these planes here, it doesn't mean that it's not also an angle in the spherical geometry of the surface.
That's right.
And so that's kind of where he's kind of missing it here.
Well, he's I thought about that too when I listened to him, and you're right. He is correct. It is actually the angle between those planes. But I would point something else out to Bev. Make those three planes orthogonal to each other, and you will have three 90-degree angles.
Yeah.
That's 270 degrees.
Yeah.
That
on the surface.
That would be 270 degrees on that surface, on that triangle that you've drawn.
Yeah. I think you don't quite go as far into the video that we're going to cover tonight, but in the latter part of this video of mine that we're watching, I do actually draw a equiangular right triangle on Google Earth, and show you that I even zoom into each corner so you can see that those lines are completely straight and making right angles on each of the 3 points. And it's just 2 points on the equator and a point on the North Pole.
Yeah.
It's not hard to produce.
Yeah, exactly. And they're orthogonal. They have to be. They're latitude lines crossing longitude lines, which always cross at right angles. All right.
Which incidentally is another proof that the Earth is spherical, right? Because you can't have that shape on a flat Earth map. If you did, like for example, the typical one that has the North Pole at the center, you tried to draw that equiangular right triangle on that, the one of the lines follows the equator, which is a circle in the flat Earth's map, and you'd have two straight lines on the flat Earth map as the other sides. But the catch is that those three sides on that equiangular right triangle that I draw on Google Earth are all the same length. They're not different lengths. All three sides are the same length. But if you draw that on, North Pole is the center and the equator or whatever, the equator line, that's an arc length in that thing, and it'll be necessarily longer than those radii. So yeah, like you can't draw this triangle on the surface, on a flat surface. The only way you can get that triangle is on a sphere.
That is the only way. You're right.
Three lines have nothing to do with this spherical triangle. So he is drawing these angles, but these angles are describing three planes, not three lines.
Well, yeah, it's describing three planes, but those three planes intersect the sphere in circles. So yeah, if you ignore everything besides the intersection, yeah, you're just talking about circles.
Yeah, you can't have an angle between a curved line and a curved line.
Yeah.
But it is,
Well, yeah, you can have an angle between a curved line and a curved line, Bill. Sorry.
Yeah, we define that using tangent lines. It's not complicated.
Not at all.
If you were to do this with a ball, a sponge ball, let's say, you could easily see that the piece that you end up with has straight sides. There you go.
That doesn't look very straight to me, Biff.
Yeah, I think he's referring to the edges.
Yeah.
For sure. But
he's ignoring
yeah,
the part.
like,
He's ignoring the part that's on the surface.
Right. Yeah. I mean, he has the other side of the object that he's showing is a spherical triangle. Like it's a triangle on the sphere on the surface of that sphere.
Exactly.
That this is cut out of.
Exactly.
But,
that's the slice through, and the angles will be measured between those planes that you've developed.
Actually,
yeah, and actually, so here's an interesting thing. If those angle measures are what he's talking about, right? Look at those three angles at the point that he's got there.
Yep.
Those don't look like they add to 180 degrees to me.
I would say they add to 270.
Yeah. But the other issue that they have is the angles that the edges are making there are not the right angles that we're talking about anyway. The angles we're talking about are in the very corners that you can see. Those would be the angles in the triangle.
Yeah, exactly.
80 degrees. In fact, it's even worse. It's not always the same sum. So to get at this idea, let's talk about how we could figure out.
It gets worse.
In fact, it's even worse. It's not always the same sum. So to get at this,
it's not always the same sum. What?
It's not.
He's saying that the sum is bigger than 180 degree, but not the same. So, for example, 200 or more.
Yeah, maybe like 3,000.
Well, so pause it there. Yeah, the 3,000 is a little outside the box. I think the largest it can be, I'd have to do the calculation in my head real quick, because I think it goes from pi to 3 pi, I think is the largest it can be. Because that would be, yeah, that's right. Because if you have, because the triangle is formed, they're going to get confused on this term lune later, but the triangle is formed by 3 lunes, or those 3 angles. Well, if you think of say all 3 edges of the triangle were a circle themselves, right? So you just pick 3 points on the triangle, and you think of those as the 3 edges. Those are making 180 degrees on each thing. That's the biggest triangle you can make. As soon as you tried to make it bigger than that, you'd end up having a triangle on the other side, kind of thing. So I think it's pi to 3 pi is the maximum area you can have. Maybe you could go up to 5 pi if you do want to if you want to allow those to be bigger than 180 degrees, then you could maybe go to the whole thing. But yeah, so maybe you go to 5 pi. Probably depends on which book you're reading in terms of whether or not they want to allow angles to be bigger than 180 degrees or not.
Yeah, right.
Yeah. This idea, let's talk about how we could figure out what the angle sum of a triangle on the surface of a sphere is.
Wow, we're going to have to figure it out. But triangles within reality are 180 degrees. We can definitely prove that. And now we're trying to figure out something else. I mean, does this sound mathematical?
Yeah, it does actually, because you can only prove that they're 180 degrees in the context of Euclidean planar geometry, which we have totally left behind. So all bets are off. You got nothing here. There's nothing you can prove here because the axioms that led to that conclusion don't hold on the surface of a sphere. And so, yeah, you've got to prove everything from scratch at that point because you're no longer in that context. So the things that were true in the other contexts are no. It's like this. Like it's like playing two different sports games, right? If you have something that's true about basketball, like shooting behind this line here that's 30 feet away or whatever, gives you 3 points, right? And then you try to apply that in a football game, right? Trying to shoot a basketball 30 feet away from some kind of goal line is going to give you, like, it doesn't make any sense, right? Curiously, they both call them field goals, I guess. But like the trying to say something about basketball in the context of basketball makes perfect sense. But trying to say something about basketball in the context of a football game, American football game, doesn't make any sense at all. And so that's basically what we have here is Euclidean geometry is one type of game and certain things work there, certain rules are there, certain things are true there. But here we have a totally different game where we're talking about the surface of a sphere that follows a different set of axioms and hence different things can be true. So you definitely need to prove new things. That is expressly mathematical. That's kind of what most of mathematics is, especially upper division stuff.
And we most definitely do figure things out in planar triangles. But we don't just draw pictures of them. We know what rules they obey.
Yeah. I mean, that's literally what Euclid was doing, was figuring all this stuff out. And interestingly enough, like the going through this as an exercise is a worthwhile thing that even Euclid would have thought, because the facts that Euclid produces in Euclid's Elements were well known. Like he didn't really prove anything new per se. Like almost every fact that he actually discusses and proves in there were things that had already been known experimentally or observationally by people just doing stuff before. Like, for example, the Pythagorean theorem was known for thousands of years before Pythagoras in different places in the world.
Oh, sure.
But it was still worthwhile to Euclid to say, hey, let's actually show why these things work or why this fact is true. And so that's what I'm trying to do here is trying to make it not so mysterious. And it turns out to not be too complicated to show that the angle sum of a triangle on a sphere is bigger than 180 degrees.
No, it's amazingly simple. Blew me away.
Yeah.
It's rather fantastic, really. And this is where the assault on the mind comes. Because this isn't something that, like somebody's forcing you to do something. This is something at the very core conception of how you understand something. Straight lines. That's what he's messing with here. How you understand straight lines in reality. And he's going to put a ball in front of you, or going to tell you, sphere, you're going to imagine ball, and then he's going to tell you that the geometry on the ball is different than the geometry of the ball.
All I have to say to there is, go ahead.
No, continue.
So what I was going to say is all I have to say here is welcome to 19th century mathematics, because that's where we figured all this stuff out. Like nothing I'm showing. Oh, actually, heck, the sphere stuff. Welcome to like 4th century BCE mathematics. Like they knew this stuff, but the talking about messing around with what straight line means or whatever, and saying that it's different in certain contexts. Middle of the 19th century is when Riemann kind of came up with, figured out how to describe that. And this I was hoping to have a video out before we did this stream, but I haven't been able to finish editing it. But I have a video coming out that's going to talk about what the deal is with Euclid's fifth postulate and the story of how Euclidean geometry led to us discovering hyperbolic plane geometry and what things look like there. And it was those kinds of discussions that I think led Riemann to think about how to generalize this stuff. And that's where we get this notion of Riemannian geometry, and that's where the stuff about geodesics and 0-second derivative stuff, like I was talking about, that's where that comes from. Those are Riemannian geometry facts that Riemann was the one who discovered, because he asked these very questions that Bev is talking about, which is, does straight always mean what we think it means? And what is it that makes something straight? And it's not clear. Like if you try to sit down and just think, like, what makes a line straight, it's not easy to define that term without also referencing the word straight. Even Euclid's attempt at trying to do it by saying that it lies evenly on itself. What does evenly mean?
Right.
Like, it's not really clear. That's just another way of saying straight.
Very strange, but let's go.
And to understand that, we first have to introduce a shape on the surface of a sphere called a lune. Now, a lune is the intersection between two great circles.
The lune.
Yeah, it is.
Lune.
That's interesting.
Yeah.
Like moon?
Wow.
Lune.
What does it mean, this name? Because
don't
I
Well, let's talk about that.
I think they
So I'm
actually
glad
go to a
that
definition.
glad we're getting into.
Yeah, he's about to go to it.
Okay, go ahead and let him hit the definition, then I'll make a comment about it.
Yeah, okay.
This kind of depth, because again, this could be just all part of the lie situation. So we'll have to take this, right? But here, let me put something. Bev, you may want to show this on the screen for the audience as well. Yeah, it's just simple Miriam.
Okay.
Now, eventually they figured out how to spell it correctly, but
Yeah. Well, and the funny thing about this is that the term, so this is pronounced lune. The lune I'm talking about is spelled Lune.
right.
Curiously, the etymology is actually similar. The reason why these words sound alike is lune was short for lunatic, which was an old term that they used for people who had, mental health challenges and stuff before they really knew anything about that stuff. And so it's not probably a very nice word to use anymore. And that's why it's turned into this, like, really highly negative connotation kind of word. But that's where the etymology came from. But the lunatic had to do with, it came from the word luna. And I think also is kind of, well, if you look up the etymology, it says that it probably had to do with lunatic, which comes from the word luna, which means moon, because they thought that had something to do with, the moon being in certain places. These are really old-timey ideas. And it also might have been partially influenced by the fact that there's a bird called a loon, which makes some really wild noises and stuff.
Yep.
And so those two things together are where this word comes from. Now, the word lune that I'm talking about, which is like an orange segment or a double orange segment on the surface of a sphere, also gets its name from moon. Its etymology comes from the same thing, because it looks kind of like, I assume, because it looks kind of like a quarter moon or something like that.
Crescent moon. Yeah. Exactly.
Yeah, exactly. So I think that's why, where it's getting its name from. It's the, but anyway, that it's just bizarre that, here we've got these guys who are.
This was just hilarious to me, though. They're going to try to.
Here we got these guys that are like really worried about linguistics and using words right or whatever, what they mean, and not realizing that there's kind of a semi-rich, etymology history between these two words, and they do share a root word, but they have nothing to do with each other once you get to this.
Nothing whatsoever.
Webster. I think that's how you spell it. Now, unless he spells it differently. So we may need to check the spelling because he's only talking. So, but there's a definition of loon. I think he said loon, correct? Did we get that right?
Say loon. What?
say it describes geometry.
There's a loon.
There it is. It looks like a crescent moon, right? It's two orange segments.
Yeah.
Not complicated.
Well, there's 4 loons, actually. 2 red ones and 2 blue ones.
Yeah. Yep,
for
absolutely.
lunatics.
What he's talking about, he's drawing lines on a ball. But he's trying to convince you that it's got something to do with another space.
That is what
It
angle
has a
that
lot to do with another
tangent
space.
forms. So let's take that for a minute, as that's the angle that's made by the loon. Well, it turns out then that if we draw 3 great circles to get our triangle, we actually create 3 overlapping loons, one for each vertex in the triangle. And the total sum of the loons cover the entire sphere. In fact, it covers some of it more than once. And that's going to be kind of an issue in just a minute. So
what?
He's just telling a story. Nothing to do with what he described just before.
The entire surface of the loons covers the entire sphere. But he's meant to be talking about triangles, not spheres. Like how... Let me hear that again, because...
loons, one for each vertex in the triangle. And the total sum of the loons cover the entire sphere. In fact, it covers some of it more than once. I was trying to make that clear by coloring it, right?
Yeah, right.
Like the first loon is the red stuff, the second loon is the blue stuff, and the third loon's the yellow stuff. And you can see that the triangle on the front gets colored 3 times. And so does the triangle in the back, although, you
can't,
drawing this as a depiction, so you can't go there. But
right. But that triangle is being covered 6 times.
Yeah, exactly. And that's going to be kind of an issue in just a minute. So what we're going to do is we're going to try to identify the area of that triangle by looking at the area of these 3 overlapping loons. So first, let's figure out what the area of a single loon is. So we go back to the idea of a loon and compute its area. Well, the region that it sweeps out is precisely the ratio of the angle measure that it has to 180 degrees. That's how much of the surface of the sphere that it's going to cover. So we'll do everything in radians here.
Right, okay, well, I'll do it. I'll give it a quick go. If those angles were to be equal, and the equal within the understanding of Euclidean logic, right, would mean that there would be 4 of them, and each of them would be equal. So there you could say quadrants.
Yeah,
that would be fair, right? But that would be us thinking of in Euclidean sort of ideas. Well, we're just talking about the orange peel bit of the quadrant, right? That's what we're talking about. Again, we're talking about it within a Euclidean framework, because I said quadrant, I said an orange. So every time you're thinking anything you think, you're thinking within Euclidean space. It's hard to
go ahead and
not
pause
think
it here.
within.
So I think Bev's just grasping at something here to try to grip some kind of understanding. And I feel kind of bad at, whenever I come across something like this, I'm like, well, maybe I should try to explain it a little better. But the scenario that's going on here, he's pointing out there's 4 different angles that you can see that these lines make. And yeah, if 4 lines intersect and they make congruent angles, they're perpendicular, and you have 90, 90, 90, 90 or whatever. Yeah, those would be quadrants. But here, the theta angle can be any size up to 180 degrees.
Right.
And if you think of the front and the back as being the part of the loon that I'm talking about, I'm not talking about the other edge. As you increase the size of that theta to 180 degrees, you're going to cover that loon, front and back, is going to cover more and more of the sphere until you get to 180 degrees where it would cover the entire sphere.
Correct.
So the portion of the sphere that the loon is covering is just the ratio of that angle theta to 180 degrees, because that's how much it's opened and swept out. And that's what I was trying to make the point here of.
Yeah, and Bev totally missed it.
Yeah.
They completely don't understand what you're getting at.
Yeah.
Euclidean space when you're doing, but you can't think otherwise. It's strange, really.
Because everything works better with that. So we take the angle measure of the loon, you divide it by pi. Now the reason why it's divided by pi and not 2 pi is because remember you have a front.
Pi is entirely Euclidean also. Goes from the relationship of the circumference to the diameter. Both of those are Euclidean. Absolutely.
So pause it there. He does this a couple of times, and he even did this when he was commenting on this video on my channel. Just because a number shows up in Euclidean space does not mean that that's the only place that number shows up, or that whenever that number shows up in some other context, that it's somehow carrying with it its Euclidean context. Pi shows up in all sorts of weird places, and it's not always in the context of a circle to its diameter, right? As a ratio. All it's doing here is just talking about angles and a radian measure or whatever. There's nothing more special about pi showing up there than the fact that 180 showed up there. But I mean, 180 is an integer. Did it suddenly make integer land come here, and that we're now talking about integers? I mean, it's really weird, the fact that he's trying to pull all of Euclidean with just the fact that this number came from there, or if I use the word angle or something, that's going to pull in all those other things, as if these things couldn't exist in other contexts as well. It's kind of very bizarre.
Yeah, that's Bev does this quite frequently.
Yeah,
he's simply trying to shoehorn his misunderstandings into one neat little package that he can claim, where he can claim everything in the world is Euclidean. My Dell monitor here is Euclidean. The car I drive is Euclidean.
Yeah. To be clear, from a mathematical perspective, right? If you say Euclidean plane, you mean a space that satisfies Euclid's 5 axioms.
Right.
If you mean a Euclidean 3 space, you'd have to have more than just Euclid's 5 axioms to settle on what that means. But that's where it's weird. Like, I don't think he even understands what it means to be Euclidean.
I have tried to get him to many times. I've tried to pin him down and get him to tell me what Euclidean space means.
Yeah.
And he won't do it.
It's pretty clear mathematically what we mean by it. We're very precise about things. And back to a lune. So if you have a lune that's as wide as pi, you have the entire sphere. If you have less than that, the angle of the lune divided by pi is the ratio of the surface area of that sphere that lune covers. If you want to find the area of that lune, you have to take that ratio, that angle measure divided by pi, and multiply that by the total surface area of a sphere, which is 4 pi r squared.
4 pi r squared. Euclidean. See the r?
Actually, it was Archimedes that came up with that one, Bev. Sorry.
I have to laugh with that too. That just because it has an r in it doesn't necessarily automatically make something Euclidean.
No.
You know, you can talk about radiuses in other contexts too, and it's just bizarre how they try to compensate for not understanding what's actually going on by reading weird things into the letters that you're even using for this kind of thing. I don't know. It's very bizarre.
Yeah, for sure.
Kernel. Pi is also the ratio of the circumference to the diameter. Totally Euclidean. So the area that he's talking about there is a Euclidean mathematical calculation. Just conceptually, you are still talking about Euclidean space.
Yes, and the starting point is where radius starts, so in the center of the sphere. So he's leaving the surface. He's not on the surface. So this area is calculated from center of the sphere. Therefore, it is not spherical geometry anymore.
That
comment.
That made no sense. No sense at all.
Yeah, it's really weird. Yeah, we are using the measure of the distance from the center to the outside as, you know, what's going on, but that's because the surface area of a sphere increases proportionally to the square of that number. I mean, when you blow up a balloon, the surface area of the balloon gets bigger, but that doesn't mean that you're suddenly including the center of the balloon when you reference that notion. Like, you're still talking about just the outside. And this is where it's weird. Like, just because a number happens to refer to a measurement that would be somewhere else does not mean that I'm including those points. The area of that sphere does not include the center point at all in that area.
That's right. Just the surface.
Yeah, just the surface. So I've got my angle measure divided by pi times 4 pi r.
Angle, Euclidean. Pi, Euclidean. 4 pi r squared, Euclidean. The square function, Euclidean. R, straight line, Euclidean.
Wait a minute. The square function is Euclidean?
Yeah. What the heck is he even talking about? Like, you can, that's a real number or integer thing, right? You can square integers. There's nothing Euclidean about integers. Like, they're just numbers.
Just a number.
You know, yeah.
Exactly.
And angles, you can have angles in any context you want. You can have angles in any kind of geometry. And there are tons of geometries that aren't Euclidean. And so it's just it's weird that he's making these gross assumptions that just because Euclid talked about angles, that suddenly no one else can talk about angles. And if you have angles at all, it must be Euclidean, as if angles can never be discussed in any other possible context. And it's very, very weird, the way that he gets it. Now, to be fair, when we do describe angles, we usually do it with tangent things and the tangent things themselves are Euclidean, but the angles themselves are referring to things that aren't Euclidean necessarily.
Yeah, but to say the square function is Euclidean is just bizarre.
Yeah, I guess maybe because it has the word square in it.
Is velocity Euclidean, Bev?
Yeah.
We get velocity squared in a lot of equations.
Right. Kinetic energy is suddenly Euclidean because it has a square function. I don't know. It's very, very weird.
It just makes no sense.
Yeah.
Entirely Euclidean.
R squared. That angle measure we'll call theta. So theta is the angle measure of the loon. Theta over pi times 4 pi r squared. Well, the pi's cancel. Guess somebody ate them. And what's left over is just the theta. So we get the area of the loon.
They didn't even laugh at my joke. I'm mostly disappointed. Of anything else, I'm disappointed about that.
I laughed. I thought it was good.
Theta r squared. Okay, now let's go back to the 3 overlapping loons that form that triangle. If the angles are theta 1, theta 2, and theta 3, the total area of the 3 overlapping loons is going to be 4 theta 1 r squared plus 4 theta 2 r squared plus 4 theta 3 r squared. But that overcounts the whole surface of the sphere. In fact, the part that gets overcounted is the triangle that's made by the 3 geodesics and a copy of that triangle in the back. And in fact, each of the 3 loons...
Oh, 2 triangles. So everything gets duplicated within this.
Yes, if we have 1 point duplicated, so we have also this.
Yeah, all 3 points get duplicated,
Yeah.
so there's actually 6 points in the distance. Duplicated.
cover both of those triangles once. So each loon has 2 triangle areas in it. If we want to cover the whole sphere, we only want to cover the triangle in the front and the triangle in the back 1 time. But since we have 3 loons covering both of those once, we actually have 6 triangles that are counted.
Good at colouring, isn't he? Look at that. Nice. He's good at colouring balls. I bet he thinks it's a 2D surface of a ball.
Yep, I do.
Brenda and flat earth math.
We only want 2, right? 1 front, 1 back. That's 2 triangles, 1 counted, but each loon counts the...
What?
How he can have front and back in 2D? Because he's talking about front and back means perspective. So
here we go again.
Yeah. Yeah, because we're viewing it in 3-dimensional space, you'll see it as a front and a back, and that's what I'm trying to describe. But if you just lived on the surface of that thing, like we do live on a sphere, and you drew 3 loons on the surface, I mean, that's pretty expensive to do, I imagine. Yeah, you would have two different triangles that are drawn out by those lines, and you wouldn't necessarily have to think front and back. You just go from one place to the other. But it's just, I don't know. It's weird. I think they're just grasping for anything, because as we'll find in a minute, they totally are completely lost on the algebra in a second. I think they're just grasping for anything they can get at.
Oh yeah, this is already way beyond their understanding, I think.
So or depth. So he is talking about 3-dimensional space.
Yeah, he's not talking about the front and back of like a plate, is he? He's talking the front and back of a ball.
Yeah. So the part
What's
of the
difference?
surface.
But I don't understand
in
that
the front
example that he just gave.
And part.
So he said he's not talking about the front and back of a plate. But does a plate not have depth? I mean, is that okay to talk about? Like the front and back of a plate is 2D, but like what if you had a piece of sheet metal or a piece of paper or whatever? Can you talk about the front and back of that and it not being 3D? I mean, I don't know what he's getting at.
I don't either. You were right in what you said. They're just grasping at anything right now.
Yeah.
They have no idea where you're going with this, and so the only thing they really can do is just try to confuse it.
Yeah. Very weird.
Part of the surface on the back.
And there's like an entire diameter space that they want to ignore in between those two. Right?
Yeah.
It's weird, that, isn't it? Like, you've got to imagine that both of them are on the same two-dimensional plane, but they look like they're overlapping each.
Well, if you want to think about it in terms of, like, you know, I could have said they're both triangles on the outside of the sphere, if you want, you know, because they really are on the same side of the sphere. It's just, you know.
Well, he said it again, the same two-dimensional plane. We're not talking about a two-dimensional plane, Biff.
Yeah.
This is not a plane.
Yeah, the idea that, yeah, exactly. Like the idea that one dimension means line and two dimension means plane and three dimension means space. That's not, like we said, that's not how we deal with dimension in mathematics. There's all sorts of squiggly things that are one dimensional, all sorts of squiggly things that are two dimensional. And even though we can't visualize them because we don't see things that way, there's all sorts of squiggly things that are 3-dimensional, 4-dimensional, 5-dimensional, 17-dimensional, whatever you want.
Yeah.
Each other. They are the same two-dimensional plane inhabiting the same space.
Supposedly. But,
hard to tell.
Just...
It's hard to tell. Fantastic, though.
The front and the back individually, and since we have 3 of them, that means the front and the back are covered 3 times each, meaning we have 6 triangles covered when we add up the 3 lunes. And
6 triangles.
Yeah, if you were following along.
Yeah, Biff.
Each lune covers each triangle twice. There's 3 lunes. 3 times 2 is 6. Seems like I counted okay there. I don't know.
Pretty sure you got it right.
I think I'm becoming a little snarky, Blue.
Fantastic.
Yeah.
We only wanted 2. So in order to get the surface area of the sphere out of this, we have to add up the surface area of the 3 lunes and then subtract off 4 of the triangles, because that's what's been overcounted. So if we take...
It sounds like a Euclidean, right, to me, that he's just getting these pieces on the outside of a sphere and adding and subtracting bits.
Do you get the idea that if you woke Bev up in the middle of the night and said bubblegum, Bev would say Euclidean?
Euclidean, yeah. It's you know, even if you were blowing a bubble with the bubble gum. It's bizarre to me, because, like, now don't get me wrong. I don't fault anybody for, you know, if this is complicated, because this is definitely requires some background to, like, understand some of the algebra that's here. So I'm not trying to be, like, rude to anybody who's struggling to understand this, but, like, this is, I think this computation is something that you could do in high school. Like, it's just
I'm quite sure of it.
Right. I mean, you're just talking about the surface area of a sphere, which is a formula that you learn in high school. So, like, you know, all this stuff is very high school. Like, I mean, maybe at most, maybe trigonometry, which not everybody does in high school. So maybe not quite high school, but pretty close. And it's just, you know, I'm kind of, you know, it's hard because you're trying to make something like this as understandable as possible. And it's just, you know, the disconnect is weird. Like, I feel bad a little bit because I, you know, maybe they're just not paying attention, but I hope that other people are seeing what, you know, what's here and trying to make this computation not mystical or magical, which they totally think it is by the time we're done with this. They even talk about, I did some kind of magic trick somewhere in there. But literally all these formulas that I've written down here are just, you know, I've derived each and every one of them. I mean, the only one I didn't is the surface area of a sphere, because I assume that's known. But everything else is, I think, pretty well derived. So it's very, very kind of disappointing that that didn't come across to them.
Yeah. I'm at a loss for why they have such difficulty with what to me seems to be just really very rudimentary mathematics. There's nothing complex about any of this.
Yeah.
Nothing.
Sounds fair enough, but it's Euclidean. Let's just take it.
Take the sum of the area of the three lunes, 4 theta 1 r squared, 4 theta 2 r squared, 4 theta 3 r squared, and subtract 4 areas of the triangle. Let's use t for the area of the triangle. That's going to equal the area of the sphere itself, which is 4 pi r squared. Now, if you notice, I have an equation here that has 4 everywhere. So I'm going to factor 4 out of both sides and divide it out. At that point, I have theta 1 r squared plus theta 2 r squared plus theta 3 r squared minus 1 triangle equals pi r squared. So if I want to find the area of the triangle, I just have to solve for t. So I'll add that t to the right-hand side, and I'll subtract that pi r squared to the other side. So on the left-hand side, you'll notice everybody has an r squared. So you can factor that out, and what you end up with is theta 1 plus theta 2 plus theta 3 minus pi quantity times r squared. Well, theta 1 plus theta 2 plus theta 3 is actually just the angle sum of that triangle. So let's replace that with the letter sigma. So what we have then is that the area of the triangle is equal to the angle sum of the triangle minus pi, that quantity times r squared.
He's got r squared.
Yes, so this is area of the plane, of the circle.
A square, right?
Yeah.
It is an area,
So
but it's
he's
not
talking
an
about
area of the
planes.
plane.
Talking about a square, which is Euclidean.
Yeah, so he is adding areas of 3 different planes or circles, let's say. This is area of the circle. So, and now he is putting this sigma, and and this sigma is all 3 angles. So this is sigma, and he is subtracting from sigma, from angle, he's subtracting number pi. I just don't understand. What does it mean?
Well, maybe we ought to tell him what it means.
Yeah. So like if you can slide back just a little bit to get the previous Blackboard screen that I had.
That one?
A little bit more. I want the one with the full equations, a little more. So this one here, just a little bit forward. Just so it gets that first line all the way down. That's going to equal the area of the sphere itself, which is 4 pi r. So pause it there. Now, so this equation here, right? I mean, this one is the one that's purely geometrical. So this equation comes entirely from the geometry. You have the first 3 terms on the left here are the areas of the 3 lunes, which are overlapping inside that triangle, right? So you like think of 3 peels of an orange slice, right? And we're trying to wrap a sphere with these 3 orange peels, right? And you've got all 3 of them. Well, the triangle is the portion where the orange peels are covering, and those orange peels are doubling up or tripling up on each of those triangles. And so if you just added the surface areas of each of those orange peels, you'd have more than the surface area of the sphere because of the tripled up overlap.
Yeah, they're laying on top of each other. Right.
Exactly. Yeah, and we only want 2 of those triangles to be counted. But since we tripled up both the front and the back, we have 6 total triangles counted when we add up the surface areas of the 3 lunes. So to get the surface area of the sphere, we have to subtract off the extra layers of those orange peels, right? So you have to subtract off 4 of those extra layers because only 2 of them are supposed to be counted. And 6 minus 2 is 4. So that's why we're taking 4 off. So the first 3 terms are just adding the surface area of the orange peels. The minus 4 triangles is getting off the excess orange peel that's tripling up on each triangle on the front and back, and they're going to get upset with me for saying front and back again, but whatever. And what you have left over is the total surface area of the sphere. So this equation is literally just describing that exact geometric idea there of 3 lunes added up, subtract off the four copies of the triangle, what's left over is the total area of the sphere. So that equation there, like that's exactly what that area is. That's a proof, if you want, of what that area of that the area of that triangle satisfies that equation. And everything else that we do from here is purely algebra. They're all algebra moves to this equation. And any way that I algebraically manipulate this equation is exactly true, as true as this line here. So the fact that this line is established from a geometric relationship and is proved, every line that follows in the algebra is also proved true as well. And as Bev said, you can't unprove a proof. This is a proof of the statement that I'm going to make. So this line here is proof from the geometry. The rest of it comes from the algebra. And I explained the algebra moves pretty carefully. So I don't, unless you want to go through each of those again, I don't think we have to. But
I don't think
unless
so
you want
either.
to.
But that's where the pi comes from in that final expression paper. Pi is right here. This is where it comes from. It's part of the.
Exactly.
It is a necessary part of the surface area of a sphere, 4 pi r squared. And we are doing it. We're working in radians, so those angles are radians now. Okay.
Yep, they are.
That makes everything work.
Yep.
Now let's move back to where we were. Let's see. Somewhere in here.
That's about right here, yeah.
And now he is putting this sigma, and and this sigma is.
Yeah, he's putting the sigma there, paper, because it's convenient to do that. He could have left it the way he had it.
Yeah.
There's no problem with that. You could just say, stop right there. Theta 1 plus theta 2 plus theta 3 minus pi times r squared is equal to the area of the triangle. So you can do that. But just to make it easy, why not just say, okay, we're just going to say that theta 1 plus theta 2 plus theta 3 equals sigma and be done with it. Now we just got one term to write. It's easy. That's what we do in math a lot, paper. We make our lives easy when we can.
Yep. All three angles. So this is sigma. And he is subtracting from sigma, from angle, he's subtracting number pi.
He's subtracting an angle that's in radians.
Yep. And the reason why it's there is that that's what the algebra of this equation that we found geometrically led to. So this equation here is proven from the geometric equation we had before. So this equation is true for that surface area of the triangle. If you want, I mean, you could, even if in Bev's context, if you don't want to call it a triangle, the region on the sphere that we're describing is this area here. Now, it is a triangle. That's what we're talking about in spherical geometry. That's what it is. But that's what this is saying, is that this is a geometric proof that region on the sphere's area is equal to this formula here.
Yep.
I just don't understand. What does it mean? Subtracting pi from
take some angles
angle.
And then take away pi. Well, I think he means that pi is the sum of 180, right? It would consider within Euclidean space, right?
Does sigma have
within a circle? Well, sorry.
Does sigma have a specific value, or is it just a random?
It's the sum of the area of it's the sum of the angles of the three. It's the sum of the angles of the three angles in the triangle. That's what sigma is.
Yeah. And does it have a specific value?
Depends on the triangle.
Depends on the triangle. In this particular case, it certainly does, but it is not a constant. It can be lots of different numbers. You change the triangle, you change the numbers.
Yeah, exactly.
Sum of theta 1 plus theta 2
the angles between
plus
the
theta 3. This is sigma.
Okay.
All three angles, it is sigma. So he reduced this adding single angles into one called sigma. So sigma, it is that's 3 theta, theta 1, 2, and 3, and all of them.
No, it's not 3 theta, paper. Those angles don't have to be the same.
Yeah.
Them, it is sigma.
Yeah, well, because for me, this is where I've got.
They're missing that it's that they're subscripts, right? So theta 1, theta 2, theta 3 are all different, potentially different numbers.
Yeah. It doesn't say that they can't be the same. They could be. but
Yeah.
they not necessarily.
Lost because I don't know whether I was messing about at the back of the class or what I was
No,
doing,
no,
but
this
I
is
can't.
just how to
I
work
missed
out
it.
the area of a sphere, and he's just portioning parts off. But like Paper says, he's added some angles together and he's minus pi, but he doesn't mean 3.14.
Actually, pause it there. I do mean 3.14. It's 3.14 radians. It's exactly what 180 degrees is. So yes, in this equation, pi is standing in for the number 3.14159 whatever. But I don't think Bev knows what a radian is. It seems lost on him here.
Yeah, it seems to be. And just keep in mind, Bev, that pi is just a convenient name, just like Alan has renamed the sum of those three angles as sigma. Pi is just a convenient way of renaming 3.1415928, whatever.
Yeah.
It's a constant. It is a number. That's all. It represents a number.
It means 180 because that's the angle sum of the triangle. Pi. Within this framework.
Yeah, I kind of understand
But at
where it's
least he
going.
got
You know,
that,
the
that I am talking about
equations.
the
You know,
angle
my
sum.
mind just goes blank.
I'm sorry. Say it again.
Sorry, go back. Well, so I was saying at least he got that part right because that I am talking about that pi is referring to the angle sum that's equal to 180, right? So I'm comparing an angle sum to that angle.
That's right.
At least understood that aspect.
Yeah.
He doesn't mean 3.14. He means 180 because that's the angle sum of the triangle. Pi. Within this framework.
Yeah, I kind of understand where he's going. You know, the equations. You know, my mind just goes blank, and I say I don't know because something happened when I was learning it. That I missed something here, and it didn't make any sense to me.
This is like an algebraic formula where you
yeah, exactly. That's the bit I didn't get.
The bit to get t, but that's
it isn't like an algebraic formula, Bev. It is an algebraic formula.
Yeah, and this is the this is the part that I don't know. I started taking this a lot less. Well, I mean, I didn't really take it that seriously to begin with, but this is the part where I found kind of a little disingenuous because I get that people struggle with different parts of math, and I'm not trying to make anybody feel bad or anything like that. Like people struggle with stuff all the time, and that's okay. But when you're talking about something like this, and you're trying to critique a mathematical idea, but you struggle to understand like basic fundamentals of the argument being made, how can you really like say that you're seriously criticizing this? Like the fact that they don't understand this calculation just makes this entire exercise rather disingenuous because it means clearly they do not understand a word of what I was trying to actually say, much less the fact that algebraic equations are precisely how you prove several things in geometry. For example, Pythagorean's theorem is an algebraic equation that is describing something that happens geometrically. If you can't handle the algebra, then it's kind of hard to accept that you are qualified to criticize a mathematical argument that's geometrical, because geometry has some algebra in it. Like you're going to use that to make arguments about the geometry. That's how we do these things. So this part here for me, I found quite disingenuous. They're not taking this very seriously and aren't willing to even try to understand what's going on. And they're not willing to like it's one thing to just not understand it and ask questions about it and try to figure out and get some help to see what's going on. But they're coming at it from a point of view like, hey, this guy's just totally wrong, and we're going to tell you why he's wrong, but we don't even understand half of what he said. And that's kind of disingenuous, you know?
Well, it's exactly how they do things, though.
Yeah.
This is not it doesn't happen with Bev and this crowd or any of the other flat earthers for that matter, strictly to do with things like this, Alan. They do it with anything, everything. They have no understanding no foundation in the topic whatsoever, yet they feel like they're, for some reason or the other, they think they're qualified to critique it, and it is simply ridiculous.
Now, I will say one of the things that I've actually kind of enjoyed about watching some flat Earth, especially flat Earth debunking content, is I'll hand it to flat earthers that they do ask some pretty good questions. The problem is that they don't actually look for an answer and don't accept an answer when there's one that's been shown to answer that question. And like that's where I think the honest inquiry should be. Like, it's okay to have a question. Like, no problem. Sure. Like, have a question. If something's weird to you, something doesn't make sense, that's fine. Ask it as a question, but be humble enough to recognize that there are other human beings out there who may have worked on that question and answered it. And not only answered that, but might have asked the next 100 questions that followed and answered those as well. Yeah. I mean, like, we have, people who do this stuff full time. I mean, this teaching math, working at a university is my full-time job. I spend all day, well, right now, because I'm the department chair, I do a lot of administrative work. So mostly I'm answering emails. But when I was teaching classes, I mean, I was solving math problems and working on math and thinking about math all day long. It's what I did full time. I didn't have any other job. I mean, that's what I did. And, so like, I was happy to answer questions to anybody who came in and actually wanted to like learn about it. But it's not the same as if, hey, you're coming in and saying, hey, I know more math than anybody here, and I'm going to tell you why you're wrong, when you clearly don't understand half of what we're even talking about. I think that's the problem I think that a lot of flat earthers have, is that they're not willing to actually recognize that maybe they haven't thought about this as hard as the scientists have, or as hard as the mathematicians have. And that maybe, just maybe it'd be worthwhile to listen and try to understand it. And that don't try to critique an argument until you fully understand it. If you come across the portion like this where you're like, wow, I have no idea what he's talking about, probably indicates you don't understand the argument. And you should go learn what this says before you try to critique it.
It would be fine if they would stop at that point and just simply say, I have no idea what this guy's talking about. And if you leave it at that, nobody's going to say anything other than, well, okay, let me see if I can help you understand it. But they don't stop there. They say, I have no idea what this guy's talking about, and I am 100% sure he's wrong.
Right. Exactly.
How do you get to that?
Yeah.
What brings you to that point? Bizarre. You don't know what's right, but you're absolutely sure this is wrong.
Yeah. This is totally in contrast to the types of classes that I tend to teach in the upper division stuff. I mean, a lot of these things are proof writing classes where people are going to be writing proofs of things. And, they have to be really careful and precise. And when you don't understand something, you have to be really honest about the fact that you don't understand it. You can tell when somebody's trying to gloss over something or whatever. They have holes in their arguments and stuff, and they have to be willing to address those things. And they get better at writing proofs the more comfortable they get at recognizing that, hey, there's some things I don't understand about this. And by the way, that's true of everybody. I mean, there's plenty of stuff about math that I don't understand, and that when I try to learn it, I have to go through those same exact motions.
Oh yeah.
Clever moving one thing from one side to the other and dividing both sides by the common factor and doing all of that sort of stuff.
Yeah, but I didn't understand. I didn't understand it. So at the time, it didn't click in my head. It doesn't click now. All I know is that he's just added up those three angles from this non-Euclidean triangle that he's just taken off that sphere, and he's called it sigma.
Yeah. Yes, but still.
And so I was wondering in my head, is he using sigma to hide the fact that he's, in a little while, he's going to say that those three angles are more than 180 degrees when you added them up, you see? Yeah. That's what I was wondering.
Well, it's got to be, and so, minus in pi from it.
Yeah.
I'm not going to hide anything.
It doesn't matter if we understand what...
Yeah, there's nothing being hidden. That's, I suppose that's just the conspiracy theorist in all of them coming out when they say things like that.
Yeah, just trying to make it convenient. I don't want to have to write θ1 plus θ2 plus θ3 because to be honest, typesetting that in the thing that I use to make this graphic is a pain.
Absolutely. Hey, I'm an engineer. We're lazy. We do things like this all the time. You math guys are no less lazy than engineers are. Hell,
Yeah.
Einstein came up with some great shit. He left out integral signs.
Oh my God. If you want to have a wild ride sometime, look up Einstein's summation convention, and it's wild how much stuff he didn't write in order to make things convenient. He would have had so. I mean, you know the capital sigma that's used for the summation notation, right?
Yeah.
He'd have had dozens of those all over the place, and he's like, I'm not doing that. He came up with a really clever way of writing it. And it does make it look incomprehensible if you don't know what the convention is, but it's pretty interesting.
Yeah. That's what I was thinking about. It was the summation sign.
Yeah.
I couldn't remember what he left out, but he left something. Yeah, that was it.
Yeah.
He's doing or not. We have, when he's closing brackets, we have R squared. And R squared means that this is area of planar area, not spherical area.
What?
They both can be R squared. I mean, like, is he refuting that the surface area of a sphere is 4 pi R squared? I mean, that's an area that's not a square. I mean, the area of a isosceles right triangle has an R squared in it if you make the lengths of the legs R. 1/2 R squared, is that a square? I mean, like, it's I don't know, the way that they're just gluing R squared to just whatever nonsense that they can see because it's the only thing they grasp is mind-boggling. It's not mathematical. It's certainly not logical or anything like that.
Just planar.
Yes, that's the main point. You've got to be able to see the relevant points. Now, what he has just done is some sort of a magic trick, right? Because he showed you a ball, a sphere. And now he's taken from that some angles. And he's just put some letters there. And he's done this thing where he does something that you relate to maths, right? Well, you don't relate to it, but you relate to it in a way that you don't relate to it, right? I'm the same.
You pause it here.
Exactly.
They were talking earlier in this video about the idea that there are so many proofs of like the Pythagorean theorem, or so many proofs that the angle sum of a triangle is 180 degrees. How do they think they prove these things? Like, have they ever read one of these things? Like, do they think that algebra never comes into play in a proof ever? I mean, it is fair. It doesn't always, but there's tons of stuff in geometry that are described through algebraic formulas. And it's the idea that you can't move to algebra in talking about a geometric proof is so far removed from how anybody does this stuff. Like, algebra is a tool that can be used to understand things. And that's what we're doing here. Like, there's no magic. This is purely algebra. Yes. It only feels like magic because they don't understand it. Like that line, any sufficiently advanced society looks like magic, right?
Yeah.
Like, any sufficiently sophisticated mathematical argument looks like magic to somebody who doesn't understand it, I guess.
Exactly
the same. Doesn't seem to be a link somewhere between him adding pi into this equation. Right now, pi is a relationship of the circle to the diameter. Well, he's got the radius here as well.
Bev, pi came from the area of a sphere. How did you miss it? That's how pi got back in this equation.
It is quite interesting, actually. If you want to do it from Bev's point of view, he is right that pi is the ratio of a circumference to the diameter of a circle.
Yeah.
It also turns out to be the ratio of the surface area of a sphere to the diameter of that sphere. But the diameter is equal to 2r, 2 radiuses, right? And if you square 2r, you get 4r squared. That's where the 4r came from. So the pi here is here simply because it actually is the ratio between the surface area of the sphere and its diameter. We just changed to talking about radii, and that's where the 4 pi came from. So the pi is coming here completely geometrically,
and just happens to be the same number that's the ratio between a circumference and diameter, that same number is also the ratio from the surface area to the diameter squared. And that's literally why it's in this equation. So it's completely geometrical why pi is here.
Good luck getting him to see that.
Yeah, I know, right?
There's pi. So does he have the diameter and the radius? Or has that got the radius square with the diameter and the circumference and the ratio of these two together?
I think I'll just refer to my previous comment.
Yeah. It's a constant, Bev. It's just a constant. That's all. We just give it a name. That's all.
Never fit with me either, because I couldn't make it work. It doesn't seem logical. It doesn't make any sense why you should be able to just say, well, the circle is pi, but pi is the relationship of the circumference to the radius, the circumference to the diameter. But then you should say pi r squared. 5 minutes left. It's going to get technical now because he's already pulled out the algebra.
Well, if you actually made a triangle, then that triangle's area is necessarily positive. Well, r squared is positive because that's the radius of the sphere. So the only possible way for the product on the left-hand side, the angle sum minus pi times the r squared, the only way for that to be positive is if the angle sum minus pi is also strictly positive. Well, this...
And that's the crux of the entire argument right there.
Right, exactly.
That's exactly
so
what
first
you were
off,
getting to. If this was a Euclidean triangle in Euclidean space, this doesn't work.
well, yeah, this formula wouldn't be true for that triangle. That's for sure.
Yeah.
The crux of the argument here is that sigma minus pi times r squared equals the area of that region of the sphere, which we're calling that triangle, right? That's what a spherical triangle is, or a triangle on the sphere. That equation, we've proven that equation is true geometrically.
Yep.
That area is equal to that thing there. Well, if one side of an equality is greater than 0, the other side of that equality has to also be greater than 0. So because the area of our triangle is necessarily positive because it's an actual area, and area is not negative, and it's certainly, you know, in this case, we're making it large enough that it's not 0 either, right? So this area is strictly positive, then the other side of that equation also has to be strictly positive. Well, you have the product of two numbers that have to be strictly positive. The r squared is one of the numbers, sigma minus pi is the other number. R squared is the square of a non-negative, is the square of a non-zero number. It's specifically a non-negative number because, as I said in the video, it's the radius. If you square a non-zero number, you get a strictly positive number. So you have a product here of two numbers. And you know the product has to be strictly greater than 0. And they're going to complain about the word strictly. That just means it's not equal to 0. So it's greater than, not greater than, or equal to. That's what strictly greater than means.
Yeah.
But so this product is greater than 0. And one of the factors of the two numbers that are being multiplied together is also greater than 0. Well, what's the only way to multiply two numbers together and get a positive number? They have to have the same sign. And if one of the numbers is positive, that means the other number has to also be positive. That's literally the logic that's here. So, you know, he's complaining about it not being logical. I'm using logical rules about how real numbers work in order to make this next statement here. So that is purely logical based off of how real numbers work.
Taking logical conclusions derived from what necessary.
Yes, but he's talking about this triangle, and this is not a triangle. He's just subtracting some area from the surface of the ball. He calls it triangle, and he's trying to prove that that he is like calculating angles in this triangle, I think. But
now, pause it there, because he makes an interesting point. Now, you could argue that there's an element of semantics here. If you argue that the word triangle only ever refers to Euclidean triangle,
then what I think his name is Paper, is that what you said his name was?
Yeah.
So if you make that claim that a triangle only refers to a Euclidean triangle, then he's right. Like this statement's still true, but it's just referring to that region on the sphere that we are highlighting, and that region has this property. But mathematicians use the word triangle to refer to anything in any geometry that's formed by what we call lines, which are the things that are the shortest that give you the shortest distance between 2 points. I mean, I'm being a little loosey-goosey. Really, it has to do with the straightest possible path that I was talking about, those derivatives and stuff.
Right.
But to be simplistic, it's the shortest distance between 2 points. That's what a geodesic is. Whenever you talk about triangles in any geometric context, you're talking about drawing it with those kinds of segments. So a spherical triangle is as much a triangle as a Euclidean one is. The only difference between the two places is the context. The sides of that triangle in a sphere are the straightest possible paths that you can have on a sphere, just like the lines in a Euclidean plane are the straightest possible lines that you can have there. They're the lines that don't turn or move only with the geometry of the space. So like the spherical triangle is every bit as much a triangle in every precise sense of that word. It's a triangle as much as the other one is. There's no reason to make a distinction there other than you want to arbitrarily emphasize that Euclidean is all you want to talk about. But that's a pretty naive way to look at it, since there's tons of other geometries that exist, some of which aren't as easily distinguishable between the two as Euclidean and spherical geometry is. For example, Euclidean and hyperbolic geometry, the Euclidean plane and the hyperbolic plane define lines exactly the same way. Like hyperbolic geometry satisfies the first 4 of Euclid's postulates and uses the definitions, the common notions. Those lines do exactly the same thing. There's no difference in how you define them. And so how do you distinguish those two things,
Yeah, that's right. It comes apart at the 5th postulate.
Yeah. Mm-hmm.
And that is what some people would say.
Yeah.
The test for Euclidean space is whether or not the 5th postulate holds.
Yeah. And that's precisely what my video that's going to be coming out hopefully this week will be about, is talking specifically about Euclid's 5th postulate and what that says about Euclidean geometry and the advent and discovery of hyperbolic geometry.
Yep. I look forward to that.
Yeah.
That's a trick, right?
Everything's a trick to you,
because
Bev.
call it
any sufficiently sophisticated mathematics looks like magic to those who don't understand it.
Yeah. Yeah, what did I say? I can't imagine your confusion when the water in the toilet disappears after you flush it. Yeah, that's
Where does it go?
Yeah, it was here a minute ago. Where did it go?
I can't see it with my senses, so it must not exist anymore.
Got to be a trick.
Yeah, it's got to be a trick.
Sigma minus pi can't be 0. And if we were in Euclidean space and triangles as proved to be 180 degrees, then that minus pi would equal 0. And he's saying it has to be greater than that.
That is true.
Yeah, to be fair, what he just said is a very true statement. If we were in Euclidean space, sigma minus pi would be equal to 0. That's exactly true. But we're not in Euclidean space right now. We're talking about something different.
Mathematical sign. Well, so he's circular logic, or reifying the answer that he wants? It just has to be bigger than it.
Yes, but this is where his calculation fails, because if sigma is totality of 3 angles, and that would be 180 degrees, and if pi is 180 degrees, it means that it has to be 0. So I cannot see where is this inferring. Where is logical inferring? How he got that it has to be greater than 0? Because from his calculations, it is that it has to be 0.
I mean, that's literally what the last 3 slides were about. You know, if you had followed along and did the algebra, you'd see that it worked. I mean, one of the equations is the first equation I write down is proved geometrically. You know, if you think there's a flaw in the logic here, find it, but there isn't one. In fact, if you want a challenge, I mean, go find any actual math professor at a university and ask them about this, and they won't. There's no flaw in the logic here. You can ask them about it, and they'll all tell you it's correct. Not that that's, I mean, that's an appeal to authority, so I guess it's not really a a thing. But if you can't find the logical error, that's what I mean. Like, go ask an expert, see if they can find a logical error. That's what I'm trying to get at.
Yeah.
Go find somebody who's an expert in logic and mathematics, so a math professor, and ask them to help you find the error in the logic. They will tell you there is no error in the logic here.
Or just ask your child who's taking high school math.
Yeah. I mean, I think this is an argument this is something I could present to at the most a trigonometry class, but I think you could probably make this argument in like a 8th or 9th grade geometry course.
Easily, easily.
Yeah, it's all based off of the surface area of a sphere. As soon as you have that, everything else can fall into place. I mean, even the argument of what the surface area of a loon is the same argument of how you find the area of a sector in a circle. It's just the ratio, right? The angle ratio to 2 pi or whatever.
That's right. If you can define the ratio of that angle to the entire circle, yeah, you can find its area very quickly.
Yeah. So if you can understand that and know what the surface area of a sphere is, I think this argument is accessible to you. I mean, I guess as long as you know how to do a little algebra too, I suppose.
Yeah, there's not a lot of algebra involved in this, but whatever.
Yeah.
From his calculations, as I can see, it has to be 0, not greater than 0.
Yeah.
No paper.
So not to interrupt them again.
Good.
So sorry, I didn't mean to interrupt you, Blue. What he's saying right here is kind of a little frustrating about this, because he's like, by my calculations, this is what it would be. He completely ignores everything else that I've said up to this point. He has not followed along. He hasn't found an error. He just says, I know what the answer is supposed to be because that's what I think it should be. And so that's what it is. So he must have an error somewhere. Now, to be fair, like, if you do know a fact and you find something that's contradictory, you should be skeptical of it. I'm comfortable with that. But then go find the error. Like, go find what the issue is. And in this case, what the issue is they're making too hard of an assumption that everything in the entire universe behaves like Euclidean geometry when they barely even know what Euclidean geometry is. And not every surface satisfies Euclidean geometry. And that's the assumption that's wrong, that's leading to their wrong calculation or their wrong notion of a fact here.
Well, let's see where he takes it.
Tells us then that the angle sum of a triangle minus pi is strictly greater than 0, or that the angle sum of that triangle is strictly greater than pi. Now,
what tells you that? Because he's just wrote it down that it has to be.
Algebra tells you that.
The algebra. Same thing we've just said about 10 times, guy. Pay attention, fellas. For the triangle to exist, it has to have an area. That area has to be positive. It can't be negative. It has to be a positive number. That's where that comes from.
Yep.
He's wrote greater than.
Wishful thinking.
Yeah. Just because he wrote greater than, that means that it has to be.
Do you know of a triangle, Bev, that has no area? Please show me one.
Well, and I think that's the thing that. Oh, go ahead.
We'd call that a point, I guess.
Yeah, and that's the thing that I think he's missing. He's claiming that I just threw that greater than up because I wanted to, because there was no reason to put that. That greater than 0 is there because of a geometric fact. that if you have a triangle that is non-zero, like an actual triangle with area where the loons don't just make a single point, because a lot of this argument doesn't follow if you don't have an actual triangle there. So we're necessarily in the scenario where you have a non-zero triangle, not one that's just a point like you were saying. So we know in this context, geometrically, that triangle has positive surface area. That is a geometric fact. All I'm doing by writing that down is representing that geometric fact with symbols. Like that's a geometric statement that the area of that triangle is greater than 0 is a geometric statement that I'm using. But he thinks that I just wrote it there because he didn't understand it. That I just picked it out of nowhere, which I understand. Like a lot of times that's how it feels when you're not following along in an argument, in a mathematical argument, that it feels like these are just coming out of thin air. But it's not. And if they would delve down into this and try to understand it a little bit more and maybe learn a little algebra, they would realize that it's not, that it's not just coming out of nowhere. Now remember, that's
strictly is an authoritative word, isn't it? Kind of says this is proof, this is definite, has to be,
Yeah,
so
it's
that's
equal to, right? The equal sign. Yeah. There's no strictly equals within mathematics.
Well, just to clarify this like ridiculous argument, this is maybe again another place where we use a little math jargon, right? So you have a greater than or equal to sign and a greater than sign. Sometimes to emphasize the fact that the greater than sign does not allow equality, we'll say strictly greater than, to make sure that it's clear that we are not allowing it to be equal to that thing. So when I say the area of the triangle is strictly greater than 0, I'm saying it's greater than 0 and it is not equal to 0. And to his point, we do sometimes say strictly equal to, again, to emphasize the fact that it is exactly equal to. It can't be something else. It's just a way of being a little bit more to emphasize the point as opposed to just saying it, and potentially being misunderstood.
Right.
But it's totally mathematical term. Like we use it in math all the time. You find it in any math textbook. Go for it.
Oh yeah.
He's sophistry. Words of the sophist.
That's me.
Well, it goes on for another hour.
Yeah.
And I do have a little bit of it. And we can listen to how confused they get as you try to show them what 1 degree of spherical excess amounts to.
Yeah.
Let's listen to it.
It is.
Well,
Yeah.
Listen to a little
Sure,
bit of
let's
it.
do it. Yeah.
Oh, I'll put a link to this in the description.
I don't get it. I don't get it.
I don't get it.
You can tell the geometry that you should be using by the amount of angles within a triangle. This guy has just said flat would have more than 180 degrees.
No, I didn't say flat would do that. I said that a sphere would have more than 180 degrees. A triangle drawn on the surface of a sphere would have more than 180 degrees. I never said a flat. In fact, I specifically said the opposite. I said a flat triangle in a flat space, like a flat Euclidean plane, would have exactly 180 degrees. I think the part that maybe you skipped over here is I was talking about how we determine curvature. And we can detect intrinsic curvature by the size of the angle sum of triangles. In fact, I've got, I don't know if you can swap to a video camera on me, but if you want, I have a couple of 3D printed models that can actually show something kind of cool about this if you want.
Yeah.
I'm gonna turn a light on in here too. The lighting in here is not great.
Oh, it looks good here.
Oh, does it look okay?
Yeah, it looks fine. But
okay, I'll just leave it there.
Okay, so after a brief pause for me to get my equipment readjusted, we're back. So what do you got?
Yeah, so wanted to talk. We were talking about you can detect curvature by the angle sum on a triangle, right? So I have here a 3D printed sphere that a colleague of mine printed out.
And you can see on this sphere, this is an equiangular right triangle. So if I can adjust so you can kind of see the outside of that line there is a right angle. And the outside of this line here is also a right angle. And then if I go up to the top, that angle is also a right angle. And so here you have a sphere, right, with an equiangular right triangle. So again, here's an example, just like in the video, of a sphere that has more than 180 degrees in a triangle. My camera stopped focusing. But so this surface is called positively curved, and we can detect that by the angle sum here being bigger than 180 degrees. But if you take another surface here, and boy, it really does not want to focus. To get that, you can cut that part out while I'm trying to get this
Yeah.
the camera to focus. Jeez. So this here is a hyperbolic paraboloid, or half of one anyway, because we cut it in half. And I've drawn a triangle on this one too. This is also built out of geodesics on here, and you can see that that angle on the end there is a right angle. And if you look at it this way, you can tell that this is an isosceles triangle. But if you look at the angles on the bottom here, those angles are definitely smaller than 45 degrees. They're congruent, but they're definitely smaller than 45. So this triangle here has less than 180 degrees because it's a triangle drawn on a negatively curved surface. And a negatively curved surface just means that it bends one way in one direction, but another way in the other direction. So this saddle point here, bends this way, but it also bends this way. So it's bending down here and up here. And that's what makes it negatively curved. And when you have a negatively curved surface, you end up getting triangles around that point that add up to less than 180 degrees, and you can detect it that way. That's kind of what I was talking about in this portion of the video that we kind of cut out. But so it's just like, that's what I'm saying. And if it's flat, then when you try to draw a triangle on it like a piece of paper, that's when you get 180 degrees. So we can detect how curved something is by the angle sum of a triangle on it, which is what I was pointing out earlier. The fact that you can draw an equiangular right triangle on the surface of the Earth and have all three sides be congruent, that shows that it's a sphere. You cannot have that geometrically on a flat piece of paper, like on a flat plane or anything like that. It is not possible to have three straight lines that are all the same distance with three right angles between them. It is not possible to do that on a flat plane. If the Earth was flat, you couldn't make such a triangle. The fact that we can make such a triangle on the surface of the Earth is a mathematical geometric proof that the Earth is a sphere.
It absolutely is. And what I'm laughing about, I'm thinking about something I said to these guys a long time ago, and they have had a lot of fun thinking they caught me in a mistake of some sort. But I said to them one time, I said, it depends on how you define things. If I want to define a square as an object that only has 90-degree internal angles, I can have a three-sided square on a sphere. I can have a four-sided square on a flat sheet of paper, and I can have a five-sided square on that hyperbolic surface.
Mm-hmm.
So it's interesting what happens when you move away from just a flat plane.
Yeah, very fascinating, very rich branch of mathematics. And I tried to explain this to them in their comments that they made on the video, that we've come a long way from Euclid. It was about 2,400 years ago. And we've learned a lot about geometry since then. And we've learned that not everything is Euclidean. To be fair, it did take us to about 2,000 years to figure out that you could have a plane that was non-Euclidean. We knew about spherical geometry, but if you take it that sense, then I guess Bev and his group are only about 200 years behind the times.
That's not too bad.
Maybe not as bad.
Let's see if I can hop back to...
turn my video off.
Yeah. And
Yeah, I brought those models out because I was going to use them for the video that I'm making.
yeah, I like those models. Those are nice.
Yeah.
So anyway, back to where we were. When all else fails, just lie about it, right, Bev? Because
Yeah.
that's what he just did.
Math. I bet Flat Earth Math helped him. Paid him for that. Non-Euclidean space. It's 2023. It has to be.
180 degrees, and it would be so imperceptible when it's small that you'd probably never be able to find something that can measure it. In fact, on the surface of a sphere, we could figure out exactly how large a triangle would have to be in order to exhibit an angle sum that's even 1 degree larger than 180 degrees. Well,
oh, here we go. You can determine through pi, probably. Probably going to do it through pi.
what we want to do is we want to have our angle sum minus pi to be 1 degree larger. We have to convert that 1 degree into radians. To convert degrees into radians, we multiply by pi over 180, which is a conversion factor because pi radians is equal to
He's making an angle. What's going on there?
180 degrees.
180 degrees. He's doing that thing for you here, Bert. What do you reckon he's doing? Turning a degree into what's he turning the degree
I'm doing
into?
something weird. I mean,
Converting degrees to radians. Yeah, that's what I think.
pretty
Yeah.
simple.
Yeah. Maybe try listening, Biff.
Can you tell?
Radians.
Yeah, but do you know
It's a
what a
radian.
radian is? Bert.
Yeah, it's the diameter line from the center to the edge of the sphere or circle.
The radian, right, is if you think of the angle as being the little bit at the center, you know, between the two straight lines. Well, a radian is the circumference of the measure of that angle. So it's the same as an angle, except it's related to the end of the radius, right? So it's the angle.
What?
To be fair, he's like 50% there.
He's almost, yeah, I know. He gets almost there and then falls off the horse.
Yeah, if you form an angle, 1 radian, the unit 1 radian for an angle is the angle in a circle that sweeps out a radius of arc length on the edge of the circle.
Right.
That's where he's getting the circumference thing from, right? So if you want, you could think of it this way. A radian is the angle, or an angle measured in radians is telling you what portion of the circle that you're sweeping out as a ratio of it to 2 pi, right? So it's like, it's on a scale from 0 to 2 pi, but if you divide by 2 pi, that's the fraction of the circle that you swept out. So it's actually measuring sort of how fast or how far around the circle you've gone.
Yeah.
It's just, it's basically the same thing. I mean, degrees does this. It tells you it in a fraction up to 360, right? So if you divide by 360, you get that same fraction.
Yeah.
So if you take an angle in degrees, divide by 360, you'll get a fraction. If you take that same angle in radians and divide by 2 pi, you get the same fraction. That's what it's meaning.
Yeah, I said,
anyway.
what did I write? I said it's an angle whose arc equals the radius of the circle.
Exactly.
That's what it is.
It's the same as an angle, except it's related to the end of the radius, right? So it's the angle measured in radians on the circumference, not just an angle in the middle.
I think he just said a radian is actually a radian.
Because it's related to the length of the radius, right? The radian is linked to the radius.
It is.
So it's
length
how
of the
they
radius,
imagine
Bev.
the circumference as being a distance.
Not related. It is.
Okay.
It's quite a clever trick, really, because you
Not
can
a trick.
imagine that the radian is different than an angle.
It's a unit conversion.
That's all it is.
If this is a trick, then talking about kilometers and converting to miles is a trick. I mean, like, it's just a unit of measurement.
That's all. Nothing more than that.
Yeah.
It differs only because if you have longer radius, then you will have longer distance of the circumference.
Oh,
But it
Jesus.
would be the same portion, the same angle. But of course, the length of that circumference, this portion of circumference, would be greater, but the angle will remain the same.
So it's the distance.
I
of the
mean, I'll
points
appreciate
between
this is
two-
probably the
between
most
two angles
genuine
where
part of this entire video commentary that they're making. They're actually trying to talk to each other to try to understand a mathematical concept. Like, if they did this the whole time, they'd actually have made some progress on this. Like, they're talking back and forth, trying to figure out what a radian is, and like, that's probably, you know, a healthy conversation to try to figure it out and piece together what they all know about it. It's too bad they didn't, like, you know, Google it, but because that might have been a little faster. But at least they're trying to figure out what this means here, and that's a good thing about this conversation. To be fair,
Yeah, and that's part of the reason I put it in here.
Yeah.
This part was not so bad.
the
Yeah,
radius.
but this is just normal Euclidean calculation, so I don't know what,
of course,
what
it's a
he's trying to
Euclidean
prove.
calculation.
Yeah, well, we could do
Everything's
it with
Euclidean, right? That's what
we
they're
could do it
saying?
with a Euclidean pencil on a piece of Euclidean paper.
This is just trying to convince you through a mathematical equation that a radian is the same as an angle. I don't know why he's using it. Why they don't use angles? Because I think it's because they want you to envisage this as a distance, right? They're getting an angle. Remember that saying? You can do fuck all with an angle. They're trying to pretend that they get a distance, right?
What? It's 2 units of measurement of angles. That's it.
Oh man.
You know, I don't know. Bev's from the UK, right?
Yeah.
I mean, it is a good thing he lives in the metric system, because, like, if he had to deal with all the conversions that we use with the imperial system we inherited from the UK, I mean, he'd go nuts. I mean, he'd be struggling. It's just as weird that 180 degrees is pi radians, that 8 ounces is a cup, or 5 milliliters is a teaspoon. I mean, like there's no difference. It's just a unit conversion.
That's all it is. That is all it is. Radians happen to be very convenient, and if it weren't for the fact that we eventually end up making things, and some guy in the shop needs to mark out an angle, we would use radians all the time for everything. But that's pretty damned inconvenient to try to use that obnoxious little pi thing to measure angles in the shop.
Yeah.
Degrees make a lot more sense.
Yep, a lot easier to delineate it out that way.
Yeah.
Tell you what, though, if you've ever seen somebody try to do calculus on trigonometric functions in degrees, it is gross.
Oh my God.
There's all sorts of conversion factors that have to be thrown in there. Like something as nice as the derivative of the sine is the cosine. Nope, it's got a conversion factor in it, because you have to deal with the fact that you changed how you're measuring the degrees. You have to, like, slow it down. It's really weird. You end up getting some weird chain rule stuff. It's very bizarre. And it's not nearly as pretty.
Yeah. I can't imagine the confusion that would ensue if I had to hear air traffic control say something like, Mooney 06 Quebec, turn left heading 2.13 radians.
Right.
What?
So there's right.
You want me to do what?
So, exactly. So what we really learn here is that there are contexts where one unit's better than another unit, and it's okay. But if you're going to talk about different units, you got to be able to convert between them, and that's what we're doing here.
Yeah, that's all.
That's what he's doing here.
So in some sense, we're actually multiplying by the number 1, just with units. So 1 degree times pi over 180 is just pi over 180. So if we take our angle sum and subtract pi, we want to get pi over 180. So a triangle on the surface of the Earth, in order to have an angle measure that's 1 degree larger than 180, so to have an angle measure of 181 degrees, would have to have a surface area equal to pi over 180 times the radius of the Earth squared,
Well, the radius of the Earth is about 3,958.8 miles. If we square that and multiply by pi over 180, we get about 273,529 square miles. That's roughly the size of Texas. So in order, there's actually a funny story about why I know this computation. So when I got to UVU, I was trying to think of fun hands-on exercises that I could do with students, trying to do something engaging. And I had this, I had just put together a few years before I built a talk that was around this idea of proving that the angle sum of a triangle and a sphere is more than 180. I mean, it's a classical proof. It's not new or anything. But I was messing around with that, and I was like, hey, we could detect the curvature of the Earth with this. And so I'm from Utah, obviously, because I teach at Utah Valley University. And in Utah, there's the Bonneville Salt Flats, which is an incredibly, I hesitate to say flat region. It's an incredibly flat part of the Earth in terms of elevation, right? So it's the same elevation all the way across. It's huge. And I was like, we could set up some large triangle, maybe with like laser techniques or whatever, to try to measure angles and lines here and see if we can get a detectable difference in the angle sum. And so I wanted to figure out how big would we have to make this triangle in order to have a detectable difference. And so I was like, 1 degree off. How big would it have to be? And I did this computation. I was like, yeah, this is probably not going to be doable on the salt flats. So it's just the salt flats aren't big enough to detect anything.
Well, with some good, actually with some good theodolites, but probably not, just simply because you won't be able to get far enough above the surface to see far enough.
Exactly. Yeah, you'd lose line of sight before.
Yeah, you're going to lose line of sight way before you get a triangle large enough. Now, you know, some of the big triangles that the geodetic surveyors have surveyed way out west. Some of those things were pretty huge, and they were able to get spherical excesses of in the arc minute range.
Right.
But you're not going to get 1 degree.
Right. Well, and this is what should really make people appreciate what's going on with why flat earthers are confused by this. The Earth is so enormously big, and the scale that we live on it is so amazingly small that these differences are imperceptible. Every one of these manifolds that we talk about, spheres, hyperbolic paraboloids, or just a hyperbolic plane, all that stuff, they all have the property that the smaller you go, the more Euclidean-like it becomes.
That's right.
And if the largest circle you can see before you go off the surface of the Earth with these massive geodetic surveys that you're talking about, can only acquire spherical excesses in triangles in the arc minute range. I mean, come on, the Earth is huge. It's supposed to look flat on a scale like that. That's what bothers me about that observation. That it's another one of those things where I'm like, listen to math, guys. Going out and looking at your visible area and saying, hey, it looks flat, that is not an observation that distinguishes a large sphere and a flat surface. You cannot tell it from there, because both a very large sphere and a flat space will look flat on the scale that you can see. So going outside and saying, hey, it looks flat to me, that means nothing. It doesn't logically distinguish between those two scenarios. It's a completely worthless argument for either spot.
Yeah, the observation that is more practical that you actually can do is measurement of reciprocal zenith angles.
Exactly.
Those can be done, and there you have enough variation that you actually can
and detect it,
even over fairly short distances of 10 or 12 miles.
Right.
Yeah.
Absolutely.
You can get 8 or 10 arc minutes of deviation in the reciprocal zenith angles, and of course, that's something else that Bev and those guys have criticized me for saying time and time again. But I can go back to the Transcontinental Survey and pull out data that was taken, and I'm talking about 150 years ago. And
Yeah.
in some of those triangles, they were measuring over distances of like 175 miles.
Mm-hmm.
Incredible as that may sound, but they do it with a thing called a heliotrope, where it's actually a mirror, so that they can see the mirror flash.
Okay.
So you obviously you're not going to see another surveyor 175 miles away, but
Right.
with a large heliotrope, yes, you can see that flash, that mirror flash.
Mm-hmm.
And in some of those cases, you get a deviation in the zeniths being not parallel with each other by a factor of 2.5 or 3 degrees. So, yeah, it's pretty impressive. And
Yeah.
if that is
And
true,
if it were flat, you'd have 0 difference.
yeah, if it were flat, there would be the reciprocal zenith angles would have to necessarily add up to 180. They don't.
Yeah.
They always add up to more than 180. Always. So
Always, yeah.
let's see what else is. Play a little bit more.
And the
of this.
radius would be Euclidean, right?
Yeah.
Because
Okay.
only the radius is Euclidean. It's a straight line. And his one is a 2-dimensional surface, so it wouldn't have a radius. The radius is Euclidean. But this is the triangle. I mean, it makes it impressive that the angle, some of the angles that these people have been measuring, that's impressive.
Well, I guess that's about all we've got. And just in the nick of time, we're coming up on 3 hours almost here. Alan, thanks so much for being with me. And I really appreciate all the effort you've put into this. Hopefully, everybody got something out of it. I don't know if we've taught the Try Thinking guys anything or not, but you never know, maybe.
Yeah. Well, I think it's more. I really appreciate being on as well. I appreciate you giving me the opportunity to chat about this a little bit. I think if even if Bev and the Try Thinking guys don't get anything out of it, hopefully other people will. Hopefully your viewers enjoy it, and they can kind of see where some of these arguments come into play, and what the math is behind it. But yeah, I really appreciate you having me on. If I can make a plug for my channel, if you guys enjoyed this, check out my channel Scholar Sauce, and subscribe there. And we have a lot of fun there. I'm trying to make as many entertaining math videos as I can. So the more support I get, the more time I can put into it. Hopefully we'll see you there.
Fantastic. Yeah, be sure to drop in and visit Scholar Sauce on his channel. A link to it will be down in the description. And don't forget to hit that like button. And with that, we'll see you guys on the next one.
Yep. See you later.